Okay, well, I'll probably have a couple more people filtering in, but I figured out what I was doing wrong with the globe last time. All right, so just taking a look as a review for the Earth. The reason why I got this incorrect, here's our North Pole, here's our mid-latitudes here, was I had the Earth rotating the wrong way. I had us going like this. That's not actually how the Earth is rotating, so it's actually going like that. Which makes sense because the sun kind of rises in the east and sets in the west here. So if we fire the missile from up here and we're hitting this target, as the missile is rising into the air, we end up hitting right here at this location, and we pull that back. This is actually where our missile hits because the Earth is rotating underneath the missile as it's traveling in its line. So this is how we're deflecting to the right. And that might seem weird because we're seeing a deflection to the left, but you have to get on that missile and ride it to its destination. So if you're actually sitting up here on this missile, you're seeing you're actually deflecting to the right. Contrary down here, if you're in the South Pole and you're shooting at the equator, as you fire that missile, the Earth is rotating underneath you. So if you pull that back, you actually hit right there. So this is a left deflection for the southern hemisphere. That's why everything rotates the opposite direction in the southern hemisphere. Does that mean the toilets rotate the opposite direction? You've probably heard that before. I don't think that is influenced by the Coriolis force. But that's why a low pressure system in the northern hemisphere rotates counterclockwise, like this, but a low pressure system in the southern hemisphere rotates clockwise. So we use the term cyclonic and anticyclonic. So is that kind of good? It's typical when you're up here talking, you've been talking for 2 hours, and all of a sudden you're just like, oh my God, I can't figure out what I'm doing wrong on this, but I just wanted to clear that up. So any questions about last time? It was a lot of building blocks, right? A lot of kind of some boring stuff mixed in with some interesting stuff. We talked about a lot about relative humidity. Let's very quickly kind of talk about, before we jump into clouds, because that's how we're going to start off today, is if this is our ground, right? And we get a little bitty bubble of air sitting on the ground, and for some reason we get it to start rising, right? We called those triggering mechanism last time. Could be a low pressure system, could be a cold front, which we're going to be talking today, could be a warm front, could be the surface heating, like the earth, the sun hitting the ground causing thermals to rise up. Could be orographic lift, us pushing air up a mountainside. Somehow we get this to start rising. As it starts rising, what happens to its pressure? We're going to cover this one more time. What is it?
You said as the air starts rising?
Yeah.
What happens to the pressure? Less?
Yes, pressure is decreasing. Pressure's going down. Because pressure's decreasing, remember this equation. What was that called? Ideal gas law. If we hold volume, number, density, and gas constant, P is roughly related to T. So holding all of these constant, if this number decreases, what happens to this number? Goes down as well, right? Remember thinking about that aerosol can. You're spraying it, and you're depleting all the stuff inside the can, and that can's getting really cold. So whenever you decrease pressure, you decrease temperature. So temperature goes down. If temperature goes down, what happens to relative humidity? Remember, actual mixing ratio was moisture dependent, and saturation mixing ratio was the amount that we can actually hold in the air before we hit saturation. So if we have low temperature, that's like the waitress bringing you a cold glass of tea and you trying to put sugar in it and you can't actually get any sugar to do it. So your limit is really, really low, which means this number is really, really small. So by decreasing temperature, you're decreasing your saturation mixing ratio. You're dividing by a smaller number right here, which means that your relative humidity does what? Goes up. So saturation mixing ratio goes down, and then relative humidity goes up, and then We go from 50% humidity to 60 to 70 to 80 to 90, and then we hit 100%. What do we call that? Starts with an S. Saturation, right? So at 100% humidity, we hit saturation. So I'll put a little dotted line right here. So this is relative humidity equals 100%. Or what's another way we can say that? Because you're not given relative humidity on ATIS. What are you given?
Dew point.
You're given dew point. So at what point are we saturated with our dew point?
Whenever the temperature hits.
That's correct. Here's our temperature, here's our dew point temperature. Your dew point temperature will never be higher than your temperature, right? So if we lower our temperature to our dew point temperature, we hit saturation. So when they're really close together, we're getting pretty close to saturation. Then whenever they are together at the same number, then we have hit saturation. So this could also be T equals TD, TD for being dew point. And then what do we make? We make a cloud. Why does it have a flat butt? Because it's on that plane, right? That's where, if you look at all the clouds outside right now, and it's kind of weird because perspective, but if you got up there, if you flew up there and got right on with the clouds, you see that they're all on the same plane. That's this dotted line right here. And remember, we called this the lifting condensation level, or the LCL is what it's colloquially called. The lifting condensation level. Why does that matter? That's your cloud base. That's your cloud base. When you're listening to ATIS and they're giving you the cloud height, 3,000 feet scattered, that's what that number is. That's what that lifting condensation level is. And then again, you have to make sure that you stay how far underneath it?
500.
500, yeah. Any questions on that? We talked a lot more about like what cooling rate for the lapse rate that we used here versus up here, all that. That can be just stayed in your notes. I don't think we'll cover too much more of that today. But just to kind of remind everybody of what we talked about last time, the building blocks. This is really the big part, understanding this process for everything that we're talking about today. All right, let's talk about clouds. All right, clouds are cool. I love clouds. Anyone know what that kind of cloud is? Doesn't look like clouds we get around here, right? Now you typically get them in more rugged terrain, very common up in Colorado, up in the Rockies. Anyone know what it's called? Some of y'all have taken this before, so maybe you remember. Lenticular clouds, yeah, lenticular clouds. And we'll cover that today. You can see some more lenticular clouds over here. So very cool cloud type. Whenever I go up to Colorado for vacation, I'm actually moving up there in September, so I'm super excited. But whenever I go up there, I'm just like taking pictures of clouds and my friends think I'm just crazy. I'm just like, look at the lenticular cloud. And they're like, all right, it's a cloud. So talking about the different cloud types, we in meteorology like to break it up into high, middle, and low. But there's also technically a fourth category it has a longer name, clouds of vertical development, right? So this is kind of like its own little category over here because it spans all of them. Now there's no numbers up here. We're not talking about altitudes. So I'm not saying that low clouds are beneath 3,000 feet and then 3,000 feet to 10,000 are middle. Don't get caught up in the numbers. Don't get caught up in the numbers, right? Because if you look up at the clouds and you see some stratocumulus, but you can't really see where like the next cloud layer is going to be, it's very hard for you to say, oh, well, that's alto and that's stratus, unless you actually see the vertical layers yourself, right? So don't get caught up in exactly the altitudes that are given for each one of these clouds. Now you'll notice some similarities in all this. High clouds generally start with cirro. or cirrus. Cirrus is actually a cloud type. That means high. And your cirrus clouds, your high clouds, are generally going to be made up of ice more than water. Because all of these clouds down here are going to be made up of liquid water droplets, like fog, stuff you'd actually see on the ground. But once you get up here into this high level, you've actually crossed the threshold where everything that should have frozen has probably frozen. What's freezing temperature? 32 degrees Fahrenheit, right? Or what's Celsius? 0 degrees Celsius. What if I told you that just because you hit freezing, that doesn't mean the water has frozen yet, right? It actually takes a little bit lower of a temperature, I shouldn't say a little bit, actually a lot lower of a temperature, to guarantee that everything has frozen. Because you can have something called supercooled liquid water. So it's liquid water that is below freezing, but has not frozen yet. And all it needs is like a little kick or like a little particle to land on. And I kind of cut this from this time I'm doing the weather scenario because I didn't think it was like super useful, but I did cover it last in March. But if you get like a little particle or something like that to trigger, to catalyze the freezing, you can instantaneously get that to freeze. There's pictures of people with like water bottles that are super cold, and you just like start messing with it and you get it to like instantaneously freeze. Anyways, so the temperature that you actually get things to have all been frozen entirely is negative 40 degrees, which is a cool number because negative 40 degrees is the same thing in Celsius and Fahrenheit. It's actually where they come together and become the same number. And then they split again. So it's just where they end up meeting. So ice, and this is more liquid water, is what they're made up of. And you actually see the difference when you look up at a cirrus cloud. It looks fibrous. It looks much different compared to the puffballs that you're used to with these other clouds here. Now, if we're talking about cumulonimbus clouds, the best kinds of clouds, right? This area here might end up being all liquid water, but then this stuff up here might end up being all ice. In the middle, you can actually get a mixture of the two. And it's that mixture of the liquid water and the ice, which we'll talk about a little bit later, is what's giving us the electrical charge generation for these storms and making them have lightning. So you won't have lightning if you have all of one or the other. All ice or all liquid won't work. You've got to have a mixture of the two to get that charge creation. So let's kind of, the other things down here, stratus typically means like blankety. If you look up and it's just this one giant mass of clouds, it's all just a blanket, we'll typically call that stratus. Cumulus kind of means puffball or individual. And I think that's it. And you can see you can have stratus anywhere in each one of these. If it's not the low level, then we typically name it for either middle or high. Stratus clouds. We've all seen this. It's actually very common to have these down here in the wintertime because we end up with a nice stratified or stable layer in the evening time and going into morning. And that has to do with the ground gets really, really cold by the time we get to the morning. So if you looked at the temperature in the morning, remember this is kind of our vertical, this was Z, this was T right here. In the morning, you'll end up with something like this. So right here at the surface, it's very cold. But then as you go up in the atmosphere, we're actually having this little inversion layer. The temperature's increasing with height instead of decreasing with height. And you'll get like a stratus layer that kind of forms right at that location. But it can't go any further because it's capped. Because at this point, it is essentially colder than the environment, so it just keeps sinking down. It can't rise and get above itself. So that's generally what this stratus means. Now, if you're flying around in this, say you go get your IR certificate, do you think it's going to be very bumpy? It's going to be actually kind of nice and chill. Especially if you get above it, but that kind of stuff scares me. I'm a forever VFR pilot, so that's, yeah, I don't mess with clouds. Stratocumulus. Strato meaning low-level clouds. Cumulus meaning you can start seeing some individual cloud puffs inside there. Generally an indication that it might not be as glassy smooth as the stratus layer was. And then we have our cumulus. We talked a lot about these last time. Remember, these are created generally from what kind of triggering mechanism? What is it? Thermals. Yep, rising thermals. Just the sun hitting the ground. Surface heating is different depending on the location, so you get these rising little bubbles of air, and they create clouds, and then they just persist until they disappear. Now, these are very innocuous, right? Good indication, though, that if you're flying, which typically, if like you're going flying today, there will be puffballs everywhere, right? So is it gonna be kind of bumpy beneath this cloud layer? Yeah, because you're gonna be riding these thermals on the underside. Now, if you get above these, how's it gonna be? It's gonna change? Yeah, it'll be a lot smoother if you can get above the clouds. And nimbostratus, the other low-level cloud layer. Difference between nimbostratus and stratus: nimbostratus are rainy. Nimbo stands for rain. They're a lot darker too than your stratus clouds. That's because the amount of water content in them, the liquid water content, is higher. Now, something we did not talk about, and it's really out of the scope of the class, but you would talk about it in a meteorology class, are the precipitation processes. What triggers precipitation? Because you can have clouds that aren't raining, right? You can have like a little puffball cumulus that all of a sudden just starts, you see like virga coming out of it, a rain that's coming out of it and evaporating before it hits the ground. So there's another process that goes into creating precipitation that we're not covering. Into the altos. Now you look up, you go outside, you look up at this. How do you know this is alto? That's kind of a trick question. You really can't, right? You really can't. Maybe you'll see some other low-level clouds. Maybe, I don't know if this is perspective, maybe this is lower than the rest of it. But again, this is kind of that, just showing you guys that don't get hung up on, oh, that's stratus or that's altostratus or low or mid-level, because sometimes it's just not something you can tell unless you can see multiple cloud layers. Altocumulus, very pretty. And then up to our high levels. Cirrus are actually one of my favorite clouds. I love seeing them. Very fibrous. What are they made out of? Ice. Yep, made out of ice. Which direction do you think the wind is in this picture? Good job, guys. Good job. Yeah, this way. Because you can see they're getting swept up and pulled this way. So the wind is actually out of, I don't know what direction we're looking at here, but we'll just say out of the east, because we're assuming we're looking north here. Use clouds like that to gauge the winds. Just like you'd use a flag on the ground, use clouds to see if you can decide what the wind speed is going to be, or the wind direction. Cirrostratus, nothing really that fancy, right? Just more blankety ice clouds. And then cirrocumulus are really, really pretty. I don't know if I have a picture of it in here, and I really should add it for future presentations, is cloud streets. Because you can see these cloud streets right here. It's like, if you're a city, you're seeing like all this grid of streets going around. Generally, cloud streets will form parallel with the wind. So if the wind is, if you look outside, and I'm just going to try and draw some perspective here. I'm terrible at drawing this perspective, but if you go outside and you see all these rows of clouds coming out of the south, so just like vertically along the south, that's a good indication that you have a south wind at that level. Does that make sense? Kind of. Right. Yes?
How do you know they're out of the south and out of the north?
That's a very good, actually I should have led with that too. You wouldn't. Yeah, you wouldn't know. But you'd know that you have some kind of a line like that. Good bet here though, in the middle of Texas, it's in summertime, like 99% chance that it's probably out of the south. But yeah, you're right. You wouldn't be able to tell, but you could know it's on the north-south line. Another cool cloud. This kind of leads into the precipitation mechanisms that we're not talking about. All of a sudden, a cloud just initiates one of those processes, and you get some precipitation starting in a central location right here, and it kind of just propagates outwards and rains this section of the cloud out. So fall streak clouds are really cool. And the big boys. Everyone loves thunderstorms, right? We get some good ones here in Central Texas. So it grows and grows and grows. So our little bubble here on the ground comes up. It hits that line. What's that line? The lifting condensation level, our cloud base, right? And then it makes this giant cloud, so the air keeps rising. Eventually it hits some sort of a barrier up here. What was that barrier? What layer of the atmosphere are we in? Start. Oh, good guess. That's actually the third one. Troposphere, right? So this is the top of the troposphere. We call it the tropopause, right? So it hits the tropopause. Above here is the stratosphere. Remember, temperature from here to here is going to be decreasing with height, unless we have an inversion. But then temperature from here up is going to start increasing with height as we go, which is what the stratosphere does. So our little bubble of air is warmer than the environment, warmer than the environment, warmer than the environment, until right here, the environment starts warming up. So now our bubble is no longer warmer than the environment, so it keeps trying to rise, but it can't. It's now colder than the environment, so it sinks. And then it just spreads out. Like that. And that's what gives us our anvil. That's the limit to how high that cloud can grow. We'll talk a little bit more about this once we get to thunderstorms here at the latter half of the day. Cool little cloud here. This is a pileus cloud. Pileus cloud. You can see this on lots of different kinds of thunderstorm types. We'll see a little bit more about this later. But this is an indication that the cloud is actually growing vertically very, very quickly. So let's say you're going flying today, and all of a sudden you start seeing some, we call it some like cumulus congestus, just a puffball, a cumulus cloud that's starting to grow vertically. And you see a little pileus cloud on the top of it. That's a good indication that things are rapidly becoming something you should really, really pay attention to. Right? So this is a good indication that this cloud is becoming very, very vertically developed. Mammatus clouds. On the underside of anvils, you'll actually get, so air rises and then spreads out laterally. And then once it gets to the outer edges of the anvil, it'll actually start sinking like this. So you'll get cold air that descends out of the anvil. And when it does that, it creates these little nodules of condensation on the underside of the anvil. And that's what these mammatus clouds are. Very pretty. Yeah. Now you might see something like this maybe at most once in your life. That's like a very amazing shot of them. Typically you'll see stuff like this. A lot of times you might have to change the saturation on your phone to be able to capture them really, really well. But I've seen these several times in Austin. And then the final of the super cool clouds are the supercells, which we'll talk a little bit about at the end of the day. You could dedicate an entire week to talking about supercells and their metrics. But essentially it's a thunderstorm that's not just persisting, it's also rotating. Like the entire storm itself is rotating because the updraft on the inside is rotating. And if you get a tornado, 9 times out of 10, it's out of one of these guys. And the last two here, these are called Kelvin-Helmholtz clouds. As a pilot, what should concern you about this is wind shear. Wind shear. This is a good indication that right at this level, you're getting a very abrupt change in wind direction or wind speed. And we talked about this a little bit earlier, but lenticular clouds. Lenticular clouds. Air hits this mountain, rises like this, and then sinks on the other side, and we get this rising motion right here. So if we have rising air, pressure's decreasing, temperature's decreasing, saturation mixing ratio is decreasing, relative humidity is going up. Eventually we hit saturation. We make a cloud, goes up and over the mountain. On the other side, we have the reverse process, which we talked a little bit about last time. We have remember the rain shadow on the other side of the Sierra Nevadas? And we get away from having a cloud at that time because relative humidity over here is actually decreasing. So you get this little wave motion, and you break it up into these little lenticular cloud formations on the mountain. And very similar process for the other stuff over here. But you really need rugged terrain for this. You need to have some sort of a forced way to get the air to start doing this. This can also happen pretty far away from the rugged terrain. Like if you go out to East Colorado, you can have air that's coming over the Rocky Mountains, coming down around Denver. But because it was doing this, inertia kind of keeps it doing this for a long period of time, maybe up like 100, 200 miles down. So even if you're going flying in eastern Colorado, it's definitely something to keep in mind that you might have some wave action to your winds.
So, Joseph, from a piloting standpoint, what are we concerned about when we see lenticular clouds?
Erratic air, yeah, turbulent air. I know when I went flying up in Colorado, the CFI that him and I went up to Leadville, he says that he pays really close attention to lenticular clouds because that just, he's not saying he didn't say it's like a super dangerous situation, but he's like, it's an, I don't want to call it like an abnormal situation, but it's something you really have to pay attention to.
It's a hazard that includes, it
yes.
has a lot more risk in it than
yeah.
you don't see.
Yeah. And that's it for clouds. All right. Any questions on that? Good. I broke the other part into one giant PowerPoint here. So we'll move into talking about frontal systems. A lot more visual today. So as a review, in the northern hemisphere, which way does a low rotate? Counterclockwise, like this. Also, if we have the ground sitting here and we have a low, a surface low, what's happening to the air laterally around the low? Which way is it going? Is it leaving the low or is it coming in? Coming in, right? So it's going like this. Where does that air go? It can't go on the ground, so it's going up. Remember the gasps, right? We've got upward moving air. That's like the whole point of meteorology, is to try and predict this right here. So this is why low pressure systems are associated with bad weather, right? So if we look at this low orientation here, let me draw a little picture here that we'll come back to occasionally. So this is the Rockies. And then I'm just going to draw a terrible Texas. Right, there's Texas. All right. And there's the Rockies kind of spreading up from New Mexico up into like Colorado Springs, Denver, et cetera, et cetera. Typically, weather makes this journey. It flows from west to east in the United States. That's just the way the prevailing winds work. And you'll get a low pressure system, we call it the Colorado low, that develops on the lee side of the Rockies. Very, very common. In fact, it's almost always in the exact same location. It's right at Boulder, right around Boulder, Denver area. So much so that one of the main atmospheric research facilities, NCAR, is right there in Boulder, right? So we call this cyclogenesis because we're creating a cyclone, because this is rotating here. And this low pressure system will form up here, and its next path kind of varies. A lot of times it'll just move straight east. Sometimes it'll come down here and influence more of the Texas area, Oklahoma, et cetera, et cetera. But in all this case, you have to kind of keep an eye of which way it's rotating and what the winds are doing, right? Because how would you describe the air down here? Moisture level, temperature, etc. How would you describe it?
Southeast part?
Yeah.
Sticky.
Sticky, good, that's good. So hot and moist, right? Very high in, we talked about it last time, actual mixing ratio. The actual mixing ratio is really, really high. Consequently, the relative humidity is probably on the higher side too, but remember that relative humidity is based on temperature and moisture, so it's kind of a tricky parameter to really talk with a lot of confidence. But high dew points and high temperatures, right? So hot, we'll just do a big blue thing here, or sorry, red. Well, I don't have blue this time, so we're gonna have a blue, that'd be great. Yeah, so we'll use this here to kind of indicate cooler temperatures. But what do you think the temperatures are up here off the Rockies? Colder. Do you think they're gonna be moist?
Dry.
Dry, right? Thank you, thank you, thank you. So we'll actually add some values here. So M for moist and T for temperate. Well, actually, we'll stick to the actual classification system. So this is maritime and then tropical. Thank you. Maritime, meaning a very moist environment because we're around a lot of water. And then T here for tropical because it's a higher temperature. But up here in the Rockies, we end up having cool or cold air, right? And then we're also on the drier side. So cooler and drier. So our low here is rotating like this. So we're bringing all this cooler, drier air down off the Rockies to the Panhandle in Oklahoma. And then once this low gets down here, we're bringing all this warm, moist air up from the Gulf up this way. Does that kind of make sense to everybody? Oh, thank you. Thank you, that'll work. So that kind of explains this picture, right? Now you can kind of get this in your mind. Maybe this low is sitting right over Oklahoma, right here. So here's Texas. Here's like West Texas. Here's New Mexico, etc. So just kind of giving you some perspective. And we're bringing all this warm, moist air up, and we're bringing all this cooler, drier air down this way. And it's this battle between cool, dry air and warm, moist air that creates bad weather. So that's why we care about frontal systems. Frontal systems are air masses that are moving into another one. So we can take a look at the next screen that kind of illustrates the point. So we can have continental polar air, continental meaning dry, polar meaning cool or cold. But you can also have Arctic air, which is going to be like super cold air up this way. Continental meaning dry, tropical meaning hot, kind of down here in this area. Maritime tropical, so you're going to have your moist air that's hot down here along the Gulf states, and the same thing over here. So again, looking at this picture, it's just a constant battle between all of these air masses moving into each other, weather patterns kind of influencing them. And that's what generally creates our weather. Any questions on this? Like any comments that you want to make? All right, so from there, we can come back to this guy. And we're going to look at this one. What's this one? It's a cold front. Typically blue. I can't say 99% of the time you're going to see it as blue. I'm just hesitant to say that like that other 1%, it might be drawn in black, right? Because it might just be a black and white image, but it's always going to be triangles. And the triangles here are pointing in the direction that the wind is going, that this air mass is moving. So down here, if we had the triangles looking like this, if this kind of extended, and our triangle looked like that, even though all of this is kind of moving in this direction, some of this air could just be moving directly south. So you have to look at that triangle and see which direction that air mass is moving itself. What's this one? It's our warm front, right? So we use half circles for this. And again, the half circles are showing us which direction the air mass itself is moving. Oh, it's actually got it. Y'all are cheating. It's up at the top right. That's okay. What were these lines? So these circles here? Isobars, right? Lines of equal pressure. So this is a low. So remember, think of this like a contour map. If you were to put like a marble or something right here, it would roll down into this low. Just kind of like a depression or I wouldn't say a valley, but like a crater here. All right, so we can move on and talk about the very first one here. Cold fronts are exciting. We love them here in Texas because it means usually we're getting into fall, right? So we're going to start getting some good severe weather moving in. It's just because we just dealt with, as we're moving into right now, like 2 months of hot, low wind scenario, which is usually what July and August are all about. It's just this like high pressure system sitting over us, causing temperatures to go up, causing wind to be really, really low, just boring stuff, which we're actually moving into this next week. So huzzah, back to triple digit temperatures. So our cold air is advancing onto this warm, moist air. Now, if cold, dry air is advancing onto actually I'll just start drawing here, is advancing onto warm, moist air, which one's more dense? The cold air, right? Cold air is more dense than hot air, and dry air is more dense than moist air. All right? So this is a two-factor right here because we got colder and dry air moving onto warm, moist air. So it's going to act like a wedge, like you'd put on a door, right? It's going to cause all this warm, moist air to rise up and over this wedge that we're creating. Look at that. Remember? Gas. What happens to temperature or pressure? Temperature?
Drops.
Saturation mixing ratio? Relative humidity? Till we hit? We make our cloud. Now, the difference here in making the little bitty clouds that we talked about earlier today and last time is this cold air advancing like this is giving this air no other place to go. And it's fast. Cold fronts are quick. They're usually moving like 45 miles per hour, 60 miles per hour, something like that. They're very, very, very fast, right? So it's giving all this air over here no other choice than being forced upwards, which is why you end up with clouds of vertical development right here. Much stronger severe weather associated with these guys. So you're getting very strong development here. You're actually getting parcels of air rising up into the levels up here where we're getting some ice formation. And that ice formation mixed with the supercooled liquid water, mixed with the water droplets, you're getting charge separation, you're creating lightning, you're creating thunder. Very cool scenario. And we'll talk about this little overshooting top here once we talk about thunderstorms. But this is why we associate bad weather with cold fronts. Now, is every cold front going to make bad weather? No. We'll get cold fronts moving through here sometimes, and all you notice is like a little bit of a wind shift. And that's all you really notice. And you might notice like a cooler air, drier air, stuff like that. But for some reason, didn't make any bad weather at all. So it's more complicated than just cold front equals bad weather. There's more variables to it than just that. The other thing is, if you're right here, chilling out, the wind direction over here is actually showing as right here. We didn't really talk about wind barbs, but if we have a station model like this, the flag here is pointing in the direction the wind is blowing from. Pointing the direction the wind is blowing from. Because remember, from is king in meteorology. We always care about where the wind is coming from. So in this case, the wind is blowing like this, from the southwest. And each one of these little flags here, if it's a little flag, like that, that means 5 knots. If it's a big flag, that means 10 knots. I'd really love to insert like a weather map like part of the class, but you only have so little time to cover all these things. So here, our wind is out of what direction?
Southeast or southwest?
Yeah, from the southwest, right? Now after this cold front blows through, what's our wind direction?
Southwest.
From the northwest, right? So on the other side of a cold front boundary, you're going to expect to have a wind shift, both in wind direction and wind speed. Very typical. And of course, temperature and dew point differences as well. Any questions on cold front? Cool.
So you said before, Joseph, that a cold front doesn't always mean bad weather.
Doesn't always mean bad weather.
So would it be safe to say from a pilot standpoint that a lack of moisture is a big key to whether or not you have or don't have bad weather?
Yeah, if you have cold, dry air advancing onto air, and that other air is very moist and typically quite hot, I would say you're almost guaranteed to have some kind of convection firing up along that line. But one of the key things is maybe it's not as moist as you'd want it to be. Maybe the dew point is just too low, so that as that cold air advances on that warm, moist air and causes this bubble of air to rise, maybe the moisture here was not high enough. The difference between temperature, because remember temperature, once we lower our temperature to dew point temperature, we hit saturation, but maybe our dew point temperature was really, really low. So instead of only having to lower our temperature this much to create a cloud, the dew point temperature down here, the moisture level was low, so we actually had to end up cooling it down this much. And maybe that cold front was just not enough to do that, to get it to do that, so we didn't end up having a cloud in the first place.
So a cold front moving through a Gulf state is going to be different than a cold front moving through Phoenix.
Yes, very different. Very different. All right, warm front. Actually, let's go back one just to kind of look at this image here. So this was our cold front advancing down this way. Our warm front here, though, is warm air advancing onto cooler, drier air. Warm front advancing onto cooler, drier air. Now, as that warm front advances, is it going to get up or is it going to get underneath that cool air and force it upwards? Can it do that? Which one's more dense? The cold air is more dense, right? So the warm air can't get underneath it. It's going to ride up over that cooler air. And that's how we get this. So warm air advancing onto cooler, drier air, it rides up over the top of it. Now what you'll notice here is if you compare the slopes, look at this slope, very gentle, compared to that slope. Almost nearly vertical, right? So this is forcing that air upwards very violently. This here is not forcing that air up over very violently. It's kind of gradually pushing it up and over. You're still getting upward moving air. So pressure's going down, temperature's going down, saturation mixing ratio is going down, relative humidity's going up. So you're still eventually hitting saturation, but you're not violently hitting saturation. You're not continuing to make this vertical cloud that has thunderstorms and stuff in it. So you end up with just kind of like moderate precipitation underneath this slope. Very dreary day, just kind of overcast, nimbostratus, very common with this kind of system. More importantly, the warm front's very slow. Maybe like 20 to 40 miles per hour. Compared to the cold front, which was like 45 to 60 miles per hour. And that causes a little bit of a problem, because that means eventually this cold front here is going to catch up to our warm front. And it's going to act like a zipper along where it catches itself. Anyone know what that's called? Bonus points if you do. It's a type of front. Go ahead. Occluded front. Very good. Very good. So any questions on warm front? You'll notice as the warm front's advancing, you're seeing like nimbostratus, altostratus, cirrostratus, cirrus. So if you look up and you see cirrus, especially if you're expecting kind of a system to move up from the south, seeing this progressively stronger cloud formation is usually a good indication that like a front is on the way. Yes?
And let me say a couple things about, from a piloting standpoint, between those two fronts, with respect to weather and how you navigate. So if you're flying into or through or attempting to fly into or through a cold front, okay? First of all, it's could be very violent weather, so don't. Okay, don't land. Okay, if those fronts move very rapidly, land, tie the airplane down, go get lunch, go get dinner, let it move through, get on the back side of it, and then continue on. Perhaps, right? Generally speaking. If you're approaching a warm front, what you're going to find is the ceilings lowering as you approach that front, and IFR conditions prevail in warm front. VFR conditions prevail in the cold front unless you're in the cloud. Okay, you can get very good visibility because of the turbulence, very good visibility. VFR conditions can be very turbulent as long as you stay out of the cloud, but very violent. So get on the ground, tie it down, let the front move through. Warm front, these things can last for days. So if you're approaching a warm front, you need to land, if you're not IFR rated, and the aircraft is not capable, you need to land and go get a hotel. If it's a cold front, land and go get lunch. Understand? Because of the way they move, the weather associated with it. Okay?
Good job, thanks. All right, so what happens when they zipper themselves? The cold front catches up with the warm front. So you have cold, dry air over here, you have warm, moist air over here, and you have cooler, drier air over here. So this is our situation. Right, we start off with this. Our cold front is trying to catch up to our warm front. So we have warm, moist air here in the middle. We'll call it WM for warm and moist, right? And as that cold front catches up with the warm front, all that warm, moist air that was stuck here in the middle has nowhere to go. It gets cut off and forced upwards because we have the zipper effect like this. Right? So these catch up to each other. So you push all this warm, moist air directly upwards. It's not even just a gentle, I wouldn't say like a strong slope like this. It has nowhere to go except straight vertically up. So what you're doing, imagine you have this rag, right? And you dip it in water, let it soak, and you pull it out, and it's just dripping with water and everything like that, but you let the dripping stop. But then you go in and you wring that rag completely dry. That's what you're doing here. You're taking all this warm, moist air and you're absolutely wringing all the moisture out of that air. And you end up with something like this. Generally not super severe weather, depending on your classification of severe. We're not talking about like tornadoes or hail or extreme lightning events, stuff like that, though you can have thunderstorms in this kind of an environment. What kind of severe weather do you think we're talking about though? Heavy rain. Heavy rain, very common with occluded fronts. In fact, this low develops over here off the east coast, lee side of the Rockies in Colorado, progresses over this way. The low will typically start getting occluded right in this area, right in the Midwest, like right on the other side of Kansas and the Missouri, like right around the Mississippi River is typically where we start getting occlusion. What do we do in this area? Like Missouri, eastward, we're in like Ohio, Indiana, agriculture, major agriculture, right? This is the breadbasket of America. Why do you think that exists? Because we have predictable, we get these lows forming every single year, some more than others, right? But in general, every single year, we're going to have these lows forming and occluding right over this location. So we get torrential rainfall here in the Midwest. Now, even though it's really, really strong rain, and that would probably wash out a lot of crops, if you know it's going to be raining heavily for certain parts of the year, you can plan ahead for that and you can mitigate it, right? So that's why occlusion fronts actually benefit the US quite significantly. Any questions? All right. What other kind of front do we have? There's two more. Stationary, that's actually the next one. A stationary front is when you have a cold, dry air mass creating this cold front right here. But then you have a warm, moist air mass down here creating the warm front. But one of two things is happening. Either they're not moving at all, so they're not advancing on each other, or they're moving parallel to each other. So you end up with this boundary right here. You can see this oscillating blue and red triangle and half circle. That means we have a stationary front present right here. So one of two things is happening. Either they're not moving at all, or they're just kind of moving parallel to each other. Any questions on that one? Conditions along this boundary, I wouldn't expect it to be as bad as warm front or as bad as cold front, but you're kind of having this little boundary where you can have, because of terrain effects, wind can be advancing onto one or the other air masses locally. So you can have areas of cloud precipitation, that kind of stuff. But it's not this one giant mass event of this cold front or bow echo moving down, advancing on the warm air.
But it can stick around a while. It can just
Yeah.
stay on that line, just bring.
Yep.
Doesn't really move.
Couple weeks ago, we had some time here in central Texas where we had a front come through and just chill and become stationary right between like Abilene and Waco. And for that entire week, every day was just constant, just storms that would fire up and just sit there and create a lot of precipitation. So, all right, and our last one, our dry line. You'll see this indicated one of two ways on maps. This is the most common way that you'll see it. Half circles, kind of a brownish orange color. That's our indication of a dry line. The other way you'll sometimes see it, maybe like 20% of the time, is just this dashed line right here. And this is really confusing because we use the dashed line in meteorology to also indicate where a trough is present.
That's the way a trough is shown on all of the aviation
Yes.
stuff we get as a dash.
Yeah. Yeah, so just if you're looking at some other weather maps, there was probably some other, this can exist to show the location of a dry line, but more often than not, this means a trough is present. And we didn't really talk about troughs or ridges, but ridges are high pressure, troughs are low pressure. So what do you think a trough's associated with? What kind of weather? Bad weather. What about ridges? Good weather. Good. So a dry line, let's say all of this is hot. It's middle of summer, right? The temperature here or around here in Austin, 110, typical, right? Temperature out here in West Texas, probably like 105. We're a little bit further away from some Gulf influences right here. We're like 105. On the other side over here, like Odessa into Roswell, also like 105. Super hot times, right? The major difference between this location and this location, though, is moisture. This is a maritime environment. So we have all this evaporation occurring with the Gulf, and this southerly flow of air is causing all this moisture to come into central Texas. But over here, it's all dry. There's no big mass of water over here for us to pull water vapor from. So dry air, moist air, but both are hot. Now we talked about that. Which one's more dense, dry air or moist air?
Dry.
Dry air is more dense than moist air, which might seem really, really weird. Because you'd think that if you have moist air, more stuff is in the air, like water vapor and stuff like that, maybe it would make it more dense. But actually, what's air made of? It's made up of oxygen, it's made up of nitrogen, made up of argon, right? If you start putting moisture into that air, you're actually putting in H2O into that air. So you're taking up slots that otherwise would have been taken up by that dry air. And H, hydrogen, where is it on the periodic table for weight? All the way up here, right? So you're taking that dry air and now you're adding a lot of hydrogen to replace some of those slots inside your little bubble of air. And hydrogen doesn't weigh a whole lot. So you're actually decreasing the density at the end of the day. So that's why dry air is more dense than our moist air. But this is very key. On severe weather days in the summer, you'll actually end up with storms that fire up right along the dry line. And because we're dealing with a very dry, hot environment, Supercells are very likely, which we'll talk about here in just a little bit. But this warm, moist air is advancing onto this cold, warm air. I had to make sure I said that right? So, I shouldn't say cold. What am I trying to say? Dry air, moist air. Temperature is the same between the two. So you're still getting essentially this warm, moist air overrunning on top of this cold air. Dang, I did it again. Dry air. Moist air overrunning onto the dry air. So you'll actually get storms firing up on this dry line. So if you're planning on crossing the dry line, something definitely to keep monitor of. But again, these thunderstorms, like especially the severe stuff, aren't going to pop out of nowhere, right? They're going to be forecasted by the National Weather Service days in advance. I mean, your chances of not knowing it if you were looking at the weather forecast ahead of time is pretty low. Any questions on this? You can also get the dry front, or sorry, the dry line advancing onto the warm, moist air, and that ends up being essentially just a cold front, just without the temperature.
I have a
Yes.
question. So only having lived in Texas for 2.5 years now, but flying for 45, I've always heard about the dry line, talk about the dry line, but it really seems to only exist in Texas, it seems like. They're always talking about it in Texas. Does it typically stay west of us here? Does it move into this?
This is, I'd say, almost the exact location it is 90% of the time.
West?
Yeah, in fact, it almost follows a little bit of a geography, because right here is the Balcones Escarpment. If you drive from Abilene to Lubbock, right around Post, how many of y'all been through Post before? I'm sorry. It smells like oil. It smells terrible. It's awful. Right, but right around that location, you'll actually see it in the distance, and you'll go up and over. It's like a big giant plateau, and you increase in elevation, I don't know, like 500 to 1,000 feet, something like that. And the dry line just loves to sit right there at that boundary. That's not to say that it can't be further west or further east. I mean, my sister lives in Abilene, so I end up in Abilene a lot, and sometimes the dry line's there, sometimes it's not.
But summertime, storms firing along that dry line are a regular event.
I would
A stationary front.
Yeah. I would even say, like, during the summertime, just like the coast has like a 10% chance of storms every day, I would say the dry line has like a 10% chance of something firing up on it every single day as well. All it takes is that warm, moist air. Instead of kind of flowing directly north like this parallel to the dry line, all it takes is for some terrain effects or something like that to push it more westward, and all of a sudden you've got air that's rising, which we care about in meteorology. So taking a look at it today, I tried to look and see if like today was a good day to look at some weather and stuff like that. It's really just boring for the next couple days. But when I did this back in early March for this class, we had a really cool event coming through. We had a low pressure system. Look at our Colorado low right here, mid-latitude cyclone, and it was advancing this way to the east. And the cold front had already caught up to our warm frontier and created some occlusion, some rain up here in Kansas. We had this cold front advancing through Texas at that time. We had a warm front advancing this way. So pretty much an ideal scenario to do a little bit of analysis on. And now this is a map showcasing pretty much the same thing, but how this kind of evolves. So we had this low. Look at all the wind down here. So these flags are all pointing that direction. So that means the wind is blowing from that direction. So it's blowing this way, which makes sense. We have a low right here. We have high pressure out here. So remember pressure gradient force, which way does it point? High to low or low to high? High to low, right? So we expect the wind to go from the high pressure to the low pressure, which is what's giving us this southerly flow of wind right here. And look at the wind's pretty strong, 25 knots, 20 knots, 20 knots, etc. Now this low is going to dig in to northern Texas a little bit as we progress through the day. So here we have a mostly south wind, but look at the wind here. Maybe you can't, maybe it's too grainy, but the wind is actually blowing from the west. So right around here, we have a little barrier. The wind over here is moving from the west. The wind here is moving from the south. So what do you think we have right here?
frontal edge.
Up front. That's our cold front. It kind of matches where our low is, right? It's coming off the low, spreading down here. So we have this clashing of wind right here. Actually, the wind's moving this way, this wind's moving this way. So we had a cold front blowing through. The wind out here in West Texas that day was crazy. Here's a little image with the radar. I think this is earlier in the day. I have another one. No, this is the only one I got. But here's our cold front. Look at this wind. It's coming from the south. The thing's pointing to the south, which means the wind's blowing this way, right? Look on the other side of the cold front. Which way is the wind blowing from? Look at the wind out here in West Texas. Gusting, I think that's 60. Gusting 60 knots. You want to go flying at 60 knots? No, not at all. I don't think y'all were flying this day at all. Yeah, gusting 22, gusting 20. It was just a really heavy, it got pretty heavy on the wind that day. So can we see, we can see the cold front multiple ways. We can see it with the radar, which we're going to be talking about here in just a little bit. We can see it with our station models here with all these numbers around the side of it. I think your aviation book will also go into like what all these numbers mean, so we don't really need to spend that much time on it. But like temperature, dew point temperature, wind, etc. So pretty neat. And that's it for frontal systems. Any questions? We'll take a quick 5. We'll come back right at the 1, so like 4 minutes. All right, atmospheric soundings. We're going to go over 2 tools here. We're going to go over atmospheric soundings. We're going to go over radar. So I think they're very useful for you guys as pilots and future pilots. So sounding's job is we launch a weather balloon from a point maybe like Corpus Christi, Dallas, something like that. And that weather balloon travels upwards. And as it's going up, it's measuring 5 different things. It's measuring temperature. It's measuring dew point temperature. It's measuring pressure. It's measuring wind speed and wind direction. Now, most importantly, the wind speed and wind direction, you don't see an anemometer or anything like the little propeller on here. It's using its GPS over time to tell you what the wind speed and the wind direction are. So it measures those 5 different variables. And those are very important to us as pilots. All right? So that sounding gets launched usually twice a day, right around 6 a.m. in the morning and then around 6 p.m. at night. Certain National Weather Service offices and locations around the United States will launch these weather balloons. Weirdly enough, there are none that get launched in Central Texas, which is a shame. Corpus Christi does one. There's some out in West Texas. But we can see the location of where all these little ones are here. So you can see no stations here in Central Texas to launch them, which is really, again, just a big shame. It's a big hole right here. But you can see all the other locations here that do it. I don't really know what the difference between the red and the blue are on this map. I think it's just like different agencies might control these red ones here, but they all launch balloons on a regular basis. And they do it according to the UTC clock and not a local time clock. So the exact local time that they do it in Corpus Christi isn't going to line up to when they do it over here in Miami, but they're doing it at the exact same time instantaneously because they're all using UTC, which y'all know what UTC is, right? UTC is essentially England time because the international, I don't call it the international date line, but that line over here, the longitude, prime meridian, there we go, thank you. The prime meridian over here that England is on and Greenwich and all that, that's the world clock. So everyone uses that time to coordinate themselves around the globe. We're here right now. We have to subtract time to get to it. So in the fall, we actually fall backwards. So we become 6 hours behind them. But in the spring, we actually spring forward and we are now 5 hours behind what they are over in England. That's the way I try and remember which way it is. Right, so we're here in Central Time Zone. We are 5 hours behind England. So that means if we have a UTC time of, let's say, 18, which we use Z, 18Z, you subtract 5 from that, so you get 1300, and 1300 in military time is 1 p.m. That's how we get our time. Now in the wintertime, when we have to subtract 6 from that, we end up with noon. Cool. So these weather balloons here, they're launched at 12Z, and then again at 0Z. So 12Z minus 5 gives us 7 a.m. And then 0Z minus 5, you have to kind of circle back around, gives us, what is that, 19Z. Or sorry, 1900, which is 7 o'clock. So those are our locations. The other thing I want to make sure that you understand is there's a difference between actual soundings and forecast soundings. Actual soundings are they launch the balloon, they actually measure what is up inside the air. Forecast soundings, they're running weather models to predict what the weather's going to be like in 3 hours, 6 hours, 12 hours, 2 days, 10 days, 30 days, whatever, right? And they're predicting all the weather variables that they can, and they're actually predicting the weather variables at different levels as well. So what we can end up with is a forecast sounding. We can say, what's the vertical weather going to look like for Austin in 10 days? That would be a forecast sounding. So I use these all the time when I go fly. In fact, before I fly today, I'm going to have a gander at the weather variables here and see what it's going to look like. This is what a sounding looks like. Now this is a forecast sounding because I pulled this from, oh no, this is not a forecast sounding. No, this is. This is a forecast sounding from Tropical Tidbits, which we're going to talk at the end. Our red line here, or I should say our line all the way to the right, is going to be our temperature. You can see our temperature line. As we go up in the atmosphere, what's our temperature doing? Decreasing, right? Once we get to this point, what's it now doing? And what's it then doing here? Decreasing. Where do you think our tropopause is? Stop me when you think it is. Yeah, I'd say like in this area, most likely. Because remember, the tropopause has a little bit of a stagnation to it. And then if we keep going up here, you're going to see that the temperature will start increasing because we'll end up being in the stratosphere. Now, what do you think the green line here is? Even though it's written up here, right? It's our dew point line. So if we have the dew point and the temperature really, really far apart like this, do you think we have any clouds in this location?
No.
No. Could you though? Is it possible there could be a cloud? Yes, it could be. Maybe you had this really moist air mass raise up from Canyon Lake or something like that, and that was enough moisture added to the environment to end up hitting some saturation points. Is it going to be widespread clouds? No, we're probably going to be talking about few. Less than scattered at the very least, right? But as we get up here, look at this. They even get further apart at this level. So even less of a chance that we have some cloud cover in this vertical layer. What about here? Yeah. This is probably, I don't remember when this was March 6th. This is probably an overcast day. Is it going to be low, mid, or high level clouds though? High. We're up here like kind of the top of the troposphere. Remember, because here's the tropopause. So this is kind of like the top portion of the troposphere. So what's our temperature up here? This is the tricky part. This is why this is called a skew T, because the temperature lines where you're actually gauging the temperature are diagonal. So here's our 0 degree line. Here's our minus 20 degree line, and these are in Celsius. So any time after right here, which ends up being around 6 to 650 millibars, what is that? I have a little hand, you can find a little handy chart to be able to look that kind of stuff up. Downloads. I downloaded it specifically so that we can kind of see, and you can have something like this. So 1013.25, which is the equivalent of 2992, right? In millibars. So if we're up in this like 650 range, it looks like we're about 3.5 kilometers up. So 3.5 kilometers times 3,300 feet to get the feet, or you can just look at it like kind of like this. So you're about 2 miles up, 3.3, roughly like 2 miles up, which is like 10,000 feet. Yeah. So right around 10,000 feet, we're expecting Where was I? Yeah, right here. Oh yeah, that's where the freezing level is. Right around 10,000 feet, right here. So any clouds above this area, we're likely to have either a mix of water and ice, or in some cases, purely ice. So if all of our saturation level, if our cloud level is up here, what kind of clouds do you think we have? Cirrus. Since it's kind of more ubiquitous, you could even probably say cirrostratus. So it's like you look up at the sky, it's overcast, but there's still a lot of sunlight coming through because it's all ice, and it's just kind of like a nice stratus cirrus level up there at the top. That's kind of how we would use this to diagnose. Any questions on how that works?
I have a
Yes.
question on so the temperature line, so you're decreasing and you're increasing there between whatever those millibars are.
Mm-hmm.
What's it cause the increase there? I mean, it's an inversion there.
It's an inversion.
So it doesn't tell you, there's no way of knowing what's causing the inversion.
No, not really. I mean, it could just be like a little air mass that blew through that happened to be warmer than the rest, or, yeah, not really any. Cool. Any questions? The blue line here is called the wet bulb temperature. It gets a little complicated, but essentially if you take the air and you wring all the moisture out of it and you condense it, the act of condension will cause effects on the temperature. So you're saying, what's the temperature going to be like if we were to remove all the moisture? That's what the wet bulb temperature is. But I wouldn't worry too much about it. Just focus on these two lines. Now, when you look at other soundings in other places, they might not be green and red. They'll probably both be black. So you just know that the dew point temperature cannot be higher than the temperature, right? So the left one is always going to be your dew point temperature.
Is that blue got to do with dry adiabatic?
Kind of. Yeah, kind of. That gets more into what these other lines are on the chart. And trust me, I would love to give a whole class on SKUTs. I think they're super cool, but trying to kind of keep it on the lower side. Not overwhelmed. The other thing you can diagnose here, look at that. What's your wind speed going to be like at all these different levels? The other thing I'd kind of want to mention here, the wind barbs, they're centered on the pressure level that they're on. So this wind barb right here, this wind flag, it's actually for this pressure level. It's kind of right in the middle. It's not where the flag originates from like it would be on a weather map. So this wind barb here is telling us at the surface, which the surface is right here. It's not the very bottom of the graph. It's right here where these kind of originate from. At the surface, we're expecting what kind of knot wind? 15, right? One big flag, one little flag. So that's 10 knots plus 5 knots gives us 15 knot winds, right? We have one more flag up here, the giant flag, the big bold one. That's 50 knots. So if you were flying up here, you'd be dealing with 60 knot winds, sustained, because this isn't counting gusts, most importantly. Everyone cool on that? I look at this all the time. Every time I go before I fly, when I'm trying to decide if I want to fly over the weekend, I'm looking at these forecast soundings, like on Thursday before I even book the plane. I'm saying, hey, what's my chances of having these lines really close together? It's probably too close. I don't want to go fly in really bad conditions or like the ceilings are 1,000 feet, something like that. So I just say, no, not going to do it. Or I look at this and say, do I really want to go fly when the surface winds are 15 knots? Because that's just surface winds. That's not counting gusts. So if the weather pattern is showing, and you can see this is actually for New Braunfels. I have the dot here. The weather pattern is showing that these guys for New Braunfels is 15 knots. And there's a big low up here, which is why all this air is kind of streaming up this way. I can count on the gusts probably being at least 5 to 10 miles per hour. So then I ask myself, do I want to go fly in 15 knots sustained, 20 to 25 mile or knot gusts? The answer usually is no, right? Leading up to the check ride, though, I didn't really have a choice. But we do these. Oh, go ahead.
How do I access these?
Oh, I will get to that at the end, definitely. There's a website called tropicaltidbits.com. It's my favorite one. It's my favorite one, and we'll kind of go over that at the very end. So we do these soundings at all different kinds of locations, and you can see that we build this picture of how these soundings look. Like right here in Dallas, we have a little close call of dew point and temperature. So we expect right here at this level that we would end up having some cloud cover. Look at Kansas. They're actually pretty close, but not super close. There might be locations around the sounding where they are a lot closer or where they're a little bit further apart. So I would expect some kind of clouds in this area, maybe not ubiquitous. Look at that. That layer is completely saturated from the surface all the way up to probably like 5,000 feet, something like that. So that's very, very overcast. So you can this is just an image kind of showing what it would look like to look at it vertically across the entire US. I'm not going to cover this. I don't think it's super useful. So yeah, I'm just going to skip it. And we can move into radar. Now radar is awesome. You've all seen radar images over your life, either on TV, something like that. This is a radar program called RadarScope. It is my favorite radar program. Now, I don't work for RadarScope. I have no ties to them, but you can get RadarScope on your phone. I think it's on Apple, but I know it's on Android because I have an Android. My favorite app. So I look at it all the time. Highly recommend it. It's like 10 bucks. You spend 10 bucks on coffee. Get yourself a useful app that you'll be able to look at all the time and diagnose what the weather's going to be like. But these colors here, you already have a gut feeling for what these colors mean, right? If we're right here in Paducah and we have this bearing down on us, what do you think the weather's about to become? Bad, right? Red and some of the other colors here, we're actually topping out the scale, getting into some of the pinks and the purples. So yeah, we're going to have some really heavy rain. We're probably going to have some hail. Undoubtedly, if we're having hail and this kind of, we call it reflectivity, these strong colors, we're probably going to have some lightning, some thunder, right? So you already have a good gut feeling for what these numbers and what these colors actually mean. So let's talk about how radar works. This is also useful because some of you guys might end up going and flying planes that have radars in the nose of your plane, right? So in that case, you're actually just looking at the little cone in front of you, and it's doing the same diagnosis here for what we're going to talk about. You'll have seen this here, right? This isn't the one out there, but this is our little radar ball. This is called a you don't have to know this, but this is called a WSR-88D. That's the kind of weather radar that we use. It is, again, another thing you don't need to know, S-band. There are different frequencies that you can send out the radar beam, and the higher number or the higher the frequency gives you more information about the cloud and the particles there. The lower the frequency, the less information. That's the number one key thing here. The lower the frequency, the further it goes. The higher the frequency, the shorter range the radar goes. And the last caveat to this is the higher the frequency, because you'd want high frequency to diagnose what the weather's doing. But as soon as it hits a cloud, it starts getting something called attenuated. Like it can't penetrate the cloud very well because there's so much stuff in the way, and it gets distracted very easily. Whereas if you have a long wave or using a low resolution, low frequency, it can actually penetrate the cloud a lot better, but your information you're gathering is not as good. Radar is a double-edged sword, which is why there's a class in every meteorology school that covers radar entirely for an entire semester, because there's so much to it. Radar is also a blend of electrical engineering and meteorology, so some of the brightest people on Earth are actually in the radar field. If you look at what the radome has on the inside, you'll see this weather radar dish. This is the actual radar. The dome on the outside protects it. Now, how does the radar work? It sends out a signal, a wave, and then stops and listens for it to come back. So that wave hits an object, be it a bird, a piece of a house flying around a tornado, a mosquito, or a rain droplet, or a hailstone. We call this a hydrometeor, a little object that's made out of hydro, so like ice, liquid water, something like that. And when it hits that object, it reflects in all directions. We call it isotropic reflection. Most importantly, though, it reflects back to the radar. So the radar sends out the signal, listens for it to come back. Based on the time it takes for that signal to come back, it can do some math and tell us how far away that object was. And based on the reflected energy that came back, it can tell us some information about that object. That's the key, reflected energy. Because what you're seeing here, the reds, the greens, that map that we looked at, that's called a reflectivity image. It's reflected energy. So it sends out that signal, listens for it, turns, sends out that signal, listens for it, turns, and it does this over and over and over and over again. And then, I'm not trying to do like a salute to a long dead dictator, but it tilts up a little bit, and then it does this whole process again, and then tilts up, and then tilts up, and then tilts up, and it tilts up to its maximum inclination, and then goes back down to the bottom. So there's an area right above the radar where we do not sample anything about anything. And we call this Dakota silence. I know, nerds, right? It's like a D&D reference, right? So it's Dakota silence, we don't actually sample anything above it. So when you look at a radar app, you can actually generally choose the tilt that you want to look at. If you want to choose to look at just the base tilt here, you're only looking at like this slice of what's happening with the weather. But in some of the more advanced radar programs, you can actually look at every single one of your tilts. The downside to choosing one of these upper tilts, though, is, you're probably skipping all this weather. You're not looking at the base of the storm. Again, caveats all over the place. And you can see the general range. Even if you're using your base tilt and your storm is like right here. Something like that. And your tornado is on the ground right there. Even if you're looking at your base tilt here, are you actually sampling that tornado? You're missing it. That's because the radar beam is gradually leaving the Earth's surface. And the reason for that, do I have an image for that? Yeah, I'll just go ahead and zoom forward. As that radar beam's going out, the Earth is curving away because of the horizon. So essentially, as we're going out, the Earth is curving away from it. But if we correct that and make it just a flat image for the Earth, we're actually seeing that the radar beam is going up out to space the further out that we are. That's a downside to the radar. There's nothing we can really do about that. So that's why we have this gap. And you can see that even 10 miles out, 120 miles out, we're now sampling 10,000 feet up. So it's pretty substantial. It's something definitely to keep in mind. That's why we have a radar network of a lot of them all across the United States. There are some very bleak areas, like especially out in the western states where, all the radars are so separated that they're really not sampling the base of storms at all if something happened to form like right in the dead zone of a bunch of different radars. And we said this kind of image, which you're used to seeing, is called radar reflectivity. It's the radar beam hitting something and that energy reflecting back at us. Larger objects reflect more energy, and larger quantities of objects reflect more energy. So if you have a hailstone, that's going to show up as red or purple. Red or even like purple. That's going to show up with like a very high energy return. If you have a 100 meter by 100 meter box of really, really, really dense precipitation, like heavy rain, that's going to reflect a lot of energy. And that's going to show up as red or even purple. Conventional radar, unfortunately, cannot tell us the difference between those two. All it's telling us is there's a lot of energy return, which is a downside. Now, over the past 10 years, we've actually changed it to where our radar beam is polarized it used to be only polarized in the horizontal direction. The wave would actually go just like this. But now the radar beam, whenever it goes out, it actually sends out a vertical polarized beam as well. So it's the combination of these two. We can now get like a little, it can sample this hailstone horizontally, and it can sample the hailstone vertically, and we can get a cross-sectional view of that object. So we can say, hey, this looks like a hailstone. What do you think a raindrop looks like? Do you think it looks like this? That's a cartoon. Raindrops don't actually look like that. They actually look like this. They're little pancakes. So we can sample it horizontally. Now these are obviously not the same scale, right? hailstone and water droplet. But we can say, hey, this thing's wider than it is tall, water droplet. Hey, this thing is actually kind of equal vertically and horizontally, hailstone. We call that polarimetric radar. So on radar scope, you can actually look at that. You can go up here to the top, and you can come down to hydrometeor classification. And this is giving you a little lookup table to say, hey, this is all like green, and then there's some red and even some pink down here. And we can come down here and see what that red is. What's the red? Hail/rain. So it's telling us there's like a mix right here at this location. So if you're here in Paducah, and this is moving at you, maybe you're north of Paducah, better go pull the car in, right? Highly recommend that app. Radar Scope. Yep. Yeah, I got Carlos on it, and Carlos sends me pictures from it all the time. All right, the other thing we can gain from radar is velocity data. So these are Doppler radars. So it measures, it hits an object, and that frequency coming back at us can be shifted. It can be red shifted, which means it's moving away from us, or it can be green shifted, which means it's moving toward us. And we can get a sense for how that velocity is actually translating. You can see here gray means 0, and this is a scale in knots up here. So the warmer colors mean it's moving away from us, 10, 20, 30, 40 knots away. And then the green or the cooler colors mean it's moving toward us, 20, 30, 40, 60 knots, right? So our radar here is right here. This is Fort Worth. And you can see this line of storms here is actually moving toward us, coming down like this. And you can see the velocity of the winds. We're getting some light blues in there. Light blues, 50, 60 miles per hour, or I should say knots. I mean, roughly at this low, it's almost the same thing, but yeah, kind of give us an indication of the wind speeds. I think the most important thing for us to use, especially if you were going to go fly today, and there was the chance of having some severe weather pop up, and you're kind of threading the needle. You're like, well, it's nice and clear right now. I'm just going to stay around the airport, maybe go out to the practice area. As soon as I start seeing weather form and stuff like that, then I'll come back and land the plane. Thunderstorms, which we're going to talk about here in just a little bit, create these little bitty outflow boundaries. So it's the cold, dry air hitting the ground, the exhaust, and spreading out laterally on the ground. And this shows up as this very faint little line along these leading edges of these thunderstorms. We were talking earlier about cold fronts. A cold front that is producing a lot of storms will be pretty self-evident. But even if we have a cold front coming through the central Texas and it's not producing any storms whatsoever, 90% of the time you can take a look at the radar and you can actually see exactly where the cold front is because you'll see the little line here, the little gust front showing up on the radar. So you can actually see where you're going to have that wind shift. So you can look at this and say, hey, well, that little gust front is up next to Waco right now. I have some time here before that hits where I can go and do some flight stuff. But then once that gust front hits, that cold front moves through, you might have a wind shift to be out of the north, maybe like 20, 30 miles per hour for a little bit until things die down a little bit. So this can serve as an indication as well to stay safe. Here's some more images. Look at these storms. So these are little storms over in Springfield. Look at our little outward moving gust front from these storms. Here we have one. This gust front's moving this way, and look at the storms firing up like on the other side of the gust front. So they're little mini fronts. You can get storms that are firing up along their boundary. Here's one I captured actually earlier this year. Lubbock had a tornado warning. And this storm, you can see the little expanding ring of the gust front leaving it. And then over here, here's Lockhart. This was actually like a couple weeks ago. We had this gust front moving through. This is what you'd be looking at. You'd be like, oh, well, I can go fly a little bit. It's nice and clear. But we have this gust front that you're seeing moving through Buda, Kyle, and then down here into to San Marcos into New Braunfels. But this gust front's advancing on us, but look at these storms firing up on the edge of that boundary. And I think that's a good time to move into thunderstorms. So last two topics here is going to be thunderstorms, and then we're going to look at what I would look at to forecast. We love thunderstorms, right? Beautiful. Especially out in West Texas, any dry environments, because then you don't have a whole lot of other mess, other storms. You get like a storm just forming up and being very isolated, so you get beautiful pictures like this. So again, why isn't it growing taller? Tropopause. Yeah, it's hitting this invisible boundary up here. That's the top of our atmosphere, the top of the troposphere. The atmosphere portion that we live in. I shouldn't say the entire atmosphere. So we'll talk about thunderstorms. We'll talk about these. We'll talk about squall lines. This is a storm system and a gust front, cold, dry air moving this way, moving toward us. And all the warm, moist air out here in front of us is causing it to go up and rise into the system and feeding it energy as it's progressing forward. Do you think the winds are going to get pretty rough? Yeah, very rough. This is a common, you were talking about cold fronts earlier. This is a very common view. Like if you start seeing something like this, you got to get on the ground. You have to get on the ground. On the other side of this, maybe like wait an hour, it'll probably be nice and clear once this thing moves through. But this is very, very severe. You're going to have insane wind shear in this system. And then we'll talk about supercells. The kings of storms. All right. Here's what you need to know for your oral. Thunderstorms have 3 different stages. You have your cumulus stage, you have your mature stage, or you're kind of developing into mature stage, and then also your dissipating stage. Now, they all start out like this, just a puffball. Y'all all walked outside today. You saw that we have some cumulus clouds out there. Today, they're very innocuous. They're just cumulus clouds. They're not forecasted to be anything other than cumulus clouds. They're just going to stay little puffballs, cotton balls up there for the entire day, right? But let's say we have a triggering mechanism come through. We have a low pressure system come through. We have a cold front come through. Usually rising thermals aren't going to be enough for this. And we don't live next to any terrain, so we don't have to worry about like orographic lift. But we have something coming through causing this cloud to want to be more than what it is, right? So we get this upward moving air. So it starts developing into actually a full-fledged storm system. Now it's going to go through several development phases between here and here. But the things I really want to point out here are this one here, the cumulus stage, is updraft dominant. It's going to start sucking up all the warm, moist air that it can find because it wants that warm, moist air to fuel itself. That's its energy. And that's what's allowing it to grow. Once we hit the mature stage, the middle stage, you can see that we have an updraft, but we also have now a downdraft. The updraft is warm, moist air, but our downdraft is going to be cold, dry air, which seems weird because we have precipitation here, so you wouldn't think it's going to be like dry air. But there's precipitation in it, but the air itself is generally going to be pretty dry. A storm does not want cold air. It does not want dry air. That will inhibit the storm. That'll actually kill the storm off. It does not want it. And then once we move into the dissipating stage, do we have an updraft anymore? Do you see an updraft? No. We are now completely downdraft dominant. And that's bad. It's killing the storm. Because let's go through this. Updraft, storm is thriving, it's growing. Here, the updraft's still there. We're still getting some gas being fed into our car. But this cold, dry air came out of the storm, hit the ground, and then spread out laterally, creating a little gust front, like we talked about here with the radar. This ring. This is all that cold, dry air hitting the ground and spreading out laterally on all sides. So it's cutting off all the energy input to all of these storms around it. That's what this is. Eventually it's going to expand outward, and our updraft here is going to get killed. So now our storm is not receiving any energy anymore. No fuel. And that's what this stage is all about. Now the storm just rains itself out. I know, that's a lot of information, but we're going to actually go through this kind of piecemeal here with a lot of pictures. Yes?
Most dangerous stage
Most dangerous stage?
for the FAA, for your written test,
Ooh,
is the mature stage.
yeah, I'd say mature.
Yeah.
Dissipating can be,
You
can
go
be
out and
strong.
Get your
Yeah.
microburst, what you get in both of them.
yeah.
Mature stage is what, if you get that on a written test, that's your answer.
Because look at what you're dealing with here. Here you're dealing with like a strong updraft, and then you could cross over into this area, and all of a sudden you're dealing with a very strong downdraft. So that's a lot for you to process and handle split second like that. Not to mention, in this stage, you're probably dealing with hail. So here's another little image, kind of showcasing the same thing. Cumulus stage, this kind of breaks up into developing stage and mature stage, kind of separates them into a little bit more. But you can see these ones are updraft dominant, updraft and downdraft, updraft and downdraft, and then your dissipating stage is completely downdraft dominant.
What's your time frame of a typical life?
That's a really good question. From here to here, 30 minutes to an hour. 30 minutes to an hour, very quick. But I also want to make a very key point here. You can go from this to full-on supercell level stuff in the right conditions in 15 minutes. I have seen a cell erupt on radar and become tornado warned in the span of 15 minutes. So when you start seeing clouds on the horizon, or even pretty close by here, and they start showing vertical development, please take it seriously. Please.
What kind of conditions would you see that in? Like where geographically does that take place?
West, so Tornado Alley, basically, like Texas up through South Dakota, very, very prominent. You can also see it in the secondary Tornado Alley, like around like Mississippi, Alabama, up into Tennessee, is actually becoming very prominent as well. But the day is going to have some very just picture perfect ingredients going into that soup. Right, you're going to have a big battle between cold air and warm air, dry air and moist air. You're going to have some pre-existing vorticity, which we call like the rotating air. We'll talk about that here in just a little bit when we talk about severe weather or talk about supercells. But yeah, picture perfect conditions. So look at some pictures of this, our cumulus stage and our developing stage. And I included the scientific names because I think they're really cool, right? Cumulus humulus, we're actually going to have a lot of this today. So you're going to go flying, you're going to see just like puffballs as far as you can see. Very stable day in a sense, right? They're not really going any higher, they're not growing into vertical development clouds. But if you're flying along underneath these guys, are you going to have some bumpiness? Yeah, because these were probably formed by what process? Rising thermals. So as you're flying along, you're going to start hitting those updrafts as they're coming up from the Earth. Here's looking from our angle. Look at their butts. What are they?
Flat.
They're flat. What's that level that they're all sitting on?
Lifting curves.
The lifting condensation level, LCL. That's your cloud base. These will develop into something called cumulus mediocris. So this is where you need to start paying attention. If you're starting to see these little puffballs start growing vertically, this is what you need to start paying attention to and take seriously. Especially if you start seeing that little pileus cloud that we saw at the top, that means it's growing vertically very strongly. Here's a picture of them existing at the same time. You have some regular, some cumulus, but you also have some mediocris that are developing. So you're flying along. Oh, I don't know if you'd be flying above the clouds, at least at this stage. But you see this? This is a good indication that the pot here, you've had the heat on for a while, and you're starting to get some bubbly stuff coming up. So this could be a day that one of these guys is going to keep going and become the next stage and the next stage. And again, how long can that occur? Or how soon can that happen? 15 minutes. We move on to cumulus congestus. This guy's really going. He's probably become completely uncapped, doesn't care what the environment tells it anymore, is now just growing full vertical. It's in charge. And once we get up here, we're starting to get maybe some ice formation. So you'll start seeing some charge separation, the electric field will start building, and then we'll get some lightning discharge. Yes?
So that chart that you showed us with the two lines, the dew point, the temperature, does that show the cloud base and cloud height of where these kind of
That's a good question. You're talking about the sounding here. Yeah, I generally try and use that for that exact purpose. There's a little, you have to do a little trick. You have to take the dew point temperature. Well, first of all, you have to take your temperature here at the ground. This is why I think like doing an actual SQT lesson would be very valuable. And maybe I'll just make a YouTube video for it. But you follow along this line right here. This is our dry adiabatic line. You follow it along up here, and then you take your dew point temperature here, and you follow one of these, you can barely see it, but one of these other little slanted lines to the right. And where they meet, that'll actually tell you exactly where the cloud base is going to be, if there are clouds. So the cloud base here would actually be, if I can kind of guesstimate it, right around right there. But do we expect a cloud base to be there?
No.
Probably not. Our dew point and our temperature here are just really too far apart. I wouldn't expect to have a cloud base there. So that's one way we can estimate it. There's also, I don't know it off the top of my head, but there's like a little formula that you can use to estimate the cloud base, which you probably know.
Yeah, you asked me that now.
Yeah.
The adiabatic collapse rate is 4.4 degrees, I think.
Yeah, we'll look it up later. Yeah, there's like a little numerical thing you can do to kind of estimate what the cloud base is going to be. But generally, when I look at this, I just generally see where we have the dew point and the temperature coming very close together, and I just assume at that level we're going to have clouds. Can I diagnose within like a couple thousand feet of where the clouds are going to be? Maybe, right? But at least gives me an idea.
So by looking at that, can you tell what kind of cloud you're going to get on that?
We kind of did that. We're saying that we were completely saturated up here, so we most likely at this level we're going to be undergoing some cirrus, some ice clouds. And since it was such a strong saturation signal here, like a very vertically deep one, we were assuming like cirrostratus, something like that. Yeah. There's some skill involved in this, and the more you look at it, the more you'll get a good feel for it. There's some more cumulus congestus. Like if you were about to go flying here at Simplify, and you saw that, like up next to San Marcos, would you actually go?
And it's blown away, and I just want to go south or east.
Do you want to go south or east? To me, this is an indication that the atmosphere is pretty primed. Unless I was very confident that whatever system is making this is definitively moving out, I'd be a little hesitant. But also, I'm only ever going to be a VFR pilot. I don't want to be one of those statistics of someone who dies to weather, so I can just say no. Now, once you become a commercial pilot, maybe you can't really say no. Maybe you have to make that call. But
you don't fly through that.
yeah, you don't fly through that.
Doesn't
But
matter what you fly.
all right, so next look at the more mature stage here. What immediately do you see? I told you to really pay attention to it. What's the gray one? Pileus cloud, look at that. Not only is this thing gigantic, right, cumulonimbus calvus, but you've got a Pileus cloud up here at the top. That means not only is it big and mean, it also means business. It's going to keep growing. It's growing rapidly. Oh, yeah. Well, there you go. Vertical development. Here's another picture. And look at this. This is the calvus portion, but we actually have an anvil behind it as well. So this is actually multicellular. Here's one cell. Here's another cell because of depth of perception. Here's another cell that's growing. And then here's one in the back. And then there's another one. So this is actually, I'm just roughly counting 5 different cells here. And the problem with this is, and we're going to talk about this here in just a little bit, but we can kind of intro it now. This is mature into dissipating, because it's already at the top, it's going to start dissipating. That gust front was advancing this way. So that created this one. It rose. Its gust front kept going. Then created this one here in the front. So this one rose. And now this one's developing. So you can see how all it takes is like one storm to form. And that gust front will then propagate outwards and create tons more along its path. This is why whenever you see one storm starting to go and becoming vertical, this can really deteriorate in the matter of like an hour. You can then have multiple cells. What about at night? Which one of these is producing lightning, probably? Maybe the one here in the back? So it's pitch black at night. You're seeing some lightning, like 20 miles off your left side. You're flying this way, you're looking out this way. You're seeing some lightning because of this very developed storm here in the back. Are you actively seeing some lightning from some of these ones that are forming closer to you? They probably haven't hit that level to where they're generating the ice or the charge separation yet. But if you keep going, thinking that you're okay, all of a sudden these guys are forming in your path, and you're going to end up getting hit by like very strong updrafts and some severe weather. So you can't just depend visually on like where you think that, just because the lightning's over there doesn't mean that's the only place where the storm is. All right. And our incus. It's called incus because you made ingots back in the day. Maybe I'll play Minecraft. You make, iron ingots and stuff like that. But you make those on an anvil, and that's what we have here. Is our massive anvil. And we've already talked a lot about why that anvil is the way it is. But this is a very fully developed storm. It's producing ice, it's producing lightning, thunder, all that kind of stuff. Likely also producing hail. Whether it's giant hail or tiny hail, there's other characteristics we have to look at for that, but producing all that stuff. Very pretty. And then onto our dissipating stage. So once our updraft dies, once our expanding gust front cuts off the updraft, and now we're left with only the downdraft, the storm will just essentially rain itself out. So all of this here, the interior of our storm, just rained itself out, and we're left with what's called an orphan anvil at the top. It's just the remnant of what used to be. What about a day like this? You're flying along, you're actually over the clouds. Maybe this is Canyon Lake, it's not, but maybe it is. Why is there a hole here of clouds?
That's where some of it precipitated out.
Maybe. Good guess.
Because it's not generating bubbles over the water.
Why aren't we generating clouds over the water?
You're not generating bubbles, right?
That's a good, yeah. I like that. Here's land. Here's water. Land has a very high specific heat. It heats up really, really fast, which means that the air bubbles are going to form over that land and rise up and form a cloud. Water has a very low specific heat. It takes a lot of, that's actually reverse, I'm sorry. Water actually has a very high specific heat. It takes a lot of energy to heat up water. I might have to sit there and pour a lot of energy into like a little glass of water for it to heat up. But I don't have to spend a lot of energy to heat up that ground or that sand or whatever this ground is here, right? So the water here is going to be cooler, and the land here is going to be hotter. So what do we end up with? Where's my black? There it is. Hot air rises. Cold air what? you make this little diagram. So you have, well, what do we call this? It's downward moving air. We had a special word that we used for that last time. Subsidence, right? So we have subsisting air coming down. So that's kind of preventing cloud formation right here over the water. Now, is the fact that there's water here actually contributing to cloud formation otherwise? Oh yeah, because we're increasing the amount of moisture in the air. But right here over our lake, we're not having any cloud formation. Look in the back. Probably not a good idea to be flying.
Unless you're up there at 40,000.
Yeah. Yeah, if I see some big boys in the distance, I'm not generally willing to bet my life on all of this staying like humilus or mediocris, you know, nothing to worry about. So, last little piece, let's talk about this guy. So if we look on the top part of the anvil of a storm, in a very particularly strong storm, the updraft here typically would hit the troposphere, or the top of the troposphere, the tropopause, and spread out laterally. But if this updraft has really, really strong inertia, it's really, really strong, it can break above the tropopause and then sink back down like this. So imagine you guys, like 3 of you, were over there, and you tried to block me as I ran past you. Now, if I'm casually walking, can you stop me in my tracks?
Yeah.
Yes. If I do full charge, now I'm not a giant guy, obviously, but do you think you'd have trouble stopping me? Yeah, I think I'd pass you guys a little bit before you could get me? That's what this is doing. This is a sign that the updraft here is really, really strong. And we're probably producing a lot of good hail with it too. Eventually, though, it's going to come back down. Because like it or not, that air that's rising is, at this point, colder than the environment. So it's going to eventually sink.
So this is going to be a satellite.
Oh, yeah, yeah. Yeah, because that's definitely in the stratosphere. So here's a view you would have. There's an overshooting top. I'm always jealous. I've seen those videos of the people in the squirrel suits that jump out and like go right alongside these cumulonimbus clouds and all that. Man, that, you know, if you threw safety out the window, I'd love to do that. That'd be so much fun. And we talked a little bit about this already, but the multi-cell thunderstorm, like you had cell 1, and it created a gust front, and that gust front caused, so this gust front is expanding out this way, and that gust front caused air to rise up in front of it, created this cell, that created a gust front out this way, caused this cell to rise up, and you just cause this effect, like all around the storm, kind of like domino effect. So, very important. And we even looked at that earlier. All the different cells that are forming. All right, squall lines. Actually, let's take a little 5. Yeah, we'll come back right at the 1. Need a big one. That's probably pretty good.
There was one of them up there that looks like an actual like trail from the airplane. Yeah, the one that's crazy.
Yeah. I'm trying to find one with actual cumulus clouds. I mean, this works pretty good. We see this set up a lot here in Central Texas. You'll get here in the morning and you'll just see lots of cloud streets coming from the south. But you made a good point. I mean, you can't really tell if it's the wind's coming from this direction or this direction. But what you might notice is when you're on the ground and the cloud streets are looking like this, they're coming like this. that maybe the ground wind is coming from the left, right? You have to remember that even though the wind is either coming this way or this way, up there, that's up there. So down here at the surface, it might not be the same.
The wind is parallel to the ash.
Yeah,
Oh, okay.
it's going like this.
I thought so. I was not too sure.
Yeah. But again, that doesn't mean that the surface wind right at the runway is matching that, because then we have, you know, that might be like 3,000 feet, 4,000, 5,000 feet difference.
Then we did a ground friction. Right?
Say what? Oh yeah, ground friction plays a big part. Yeah.
Thank you.
Yeah. But I will say that if you look up and you see this, and then you're feeling wind perpendicular to it, that should immediately throw like wind shear into your mind, because you don't know when that wind shift is going to occur. Maybe it's like 1,000 feet above the runway. Maybe it's like 500 feet above the runway. So
So if you're a sailplane pilot, you look for those cloud sheets. You're right under, and that's just
yeah.
fly those streets. Awesome.
You can get really detailed with their formation, but there's more to it. All right. Almost got people. Okay, so squall lines. We've got a vertically developed storm. Maybe it's on the leading edge of a cold front. That cold front is advancing and through West Texas, and now we're in like Central Texas area right here. So we have a very mature storm. The storm's moving that direction. There's also a gust front leading the storm because we've dropped all that cool, dry air down and is spreading out laterally, some of it, most of it in front of the storm. And it's kind of self-perpetuating, right? Because we're taking all this warm, moist air over here and making it rise up and creating new cells as we're propagating this way. So it's kind of self-powered in a way, just progressing that direction. The key thing here with squall lines, though, is the wind. The straight line winds can be incredibly strong. 60 plus miles per hour, like 60 to 100 miles per hour. And that's because of this, right? And generally you'll see some Amadas on the other side, very, very pretty stuff. These can produce pretty decent hail. Generally not tornadoes though. Not out of a regular squall line. Generally not tornadoes. We also call this the convective area because it's where all the air is moving upwards. And then down here is our downdraft area. That's where all the air is moving downward. That's where the precipitation is falling. The downdraft is created through a bunch of different ways. A lot of it's just it uses up that air, that warm, moist air, so all that's left is cold, dry air, so that cold, dry air sinks. But also, once we start generating precipitation, how many of y'all have stood next to a road and like a truck drives by? What happens to the air behind that truck? Kind of goes along with the truck, right? So as that precipitation is falling, it's pulling all that air down with it. So we call that precipitation loading. So there's a picture of a squall line. Very pretty. This is called an Arcus cloud. The Arcus is the general term. You've probably heard like roll cloud or shelf cloud before. Those are both Arcus clouds. This would be more of a, kind of looks more like a roll cloud. Really not much, I wouldn't, like if you see a shelf cloud versus a roll cloud, I wouldn't say there's much difference to be expected. The roll cloud just generally has a little bit more circulation here with the gust front than a shelf cloud does. But that doesn't really mean anything to you in the long run. But if we look on radar to see what a squall line looks like, this is most assuredly the outer edge, the edge of a cold front advancing into Central Texas here. Because look at our winds. From the south, pretty strong. And if we have strong south winds, on the order of like 25 knots, 15 knots down here. We're bringing all this warm, moist air up from the Gulf, and this thing is eating well. It's at Thanksgiving dinner. It's eating all that warm, moist air and absolutely loving it, because all this air over here is just cold and dry. Maybe cold. We can't really say for certain because we don't have temperature stuffs on here, but definitely dry. But you can see, look at the wind direction on the other side. It's coming from the west. So that's what our squall line looks like. We can take this a step further though, and we can have bow echoes. Think of bow echoes like very, very strong sections of a squall line that the winds are even stronger, and we can start producing some tornadoes. Now that's a shelf cloud. So here's what a bow echo looks like. They can be standalone, kind of like this one is here, but they can also be embedded inside larger squall lines. But you can see how this section here is bowing out. And that's because the winds right here are very, very strong, so it's pushing this portion of the storm further than the ones on the outside. Now the other thing to keep in mind here is inflow from our storm looks like this. Here's the direction our storm is moving, so the wind is blowing this way. It can actually hit this storm and kind of wrap around to either side. See the little bits of rotation indicated here? There's like a little eye right there as well. So this is called a bookend vortice. A vortice being a spinny portion. And then the bookend, back when people actually had libraries, which maybe y'all still do, but you have to get these bookends to put on all the side of your books to keep them upright. Right? So that's where we get the bookend from. You can generally get like EF0, remember it goes EF0 to 5 for tornado strength. You can generally get like EF0, EF1s to spin up very briefly out of this. Nothing super serious like EF4s, EF5s, but you can get some pretty decent stuff. The big thing here though is the wind. I mean, the wind is going to be 100 mile per hour. Like 90 plus is what I would expect. And the hail can be pretty monstrous. Yes?
I have a question about squall line. I've always, so a squall line, you're referring to the squall line as that leading edge of the front itself. I've always talked about a squall line as kind of ripple effect out ahead of the front. Is there, do you refer to both the same way, or am I thinking about it, talking about it wrong?
We can talk about that a little bit more after. Typically, you're like the actual boundary of our squall line here will match up very nicely to where the temperature or the wind shift is going to be.
What do you call the storms that can occur ahead of, and they can have the same kind of intensity and stuff as the front? Because I want to say in the aviation weather publications, they talk about squall lines occurring ahead of the front.
You can't have
all of the same kind of associated bad weather,
yeah.
But it's not the actual front yet.
Given the conditions, you can have discrete supercells that will develop ahead of the cold front, especially if the situation's proper. So maybe there, but you can get some storms to form up on the initial side of it. But I mean, your main density difference between cold temperature and dry air is going to be right on that boundary of the cold front.
From a meteorological standpoint, when you, as a meteorologist, talks about squall line,
I'm talking about this.
That point,
yeah, I'm talking about this exact point. Okay. There can be some, like you could actually have the squall line back up a little bit. Yeah. So you could have some space between where the actual gust front is and the squall line itself. But yeah, I would say when I refer to a squall line, I mean the actual convective line of the storms. Yeah. All right, supercells. Supercells rotate. Supercells rotate. The whole thing is rotating. It's not just a standalone regular thunderstorm just sitting there growing and then dying, right? How long did we say a normal thunderstorm lasts? Yeah, I'd say like 30 minutes to an hour, maybe an hour at the most, right? From like inception, from going from a cumulus cloud all the way to the mature stage and then dying off. Probably in like the 30 minutes to like an hour range. But it can go from cumulus to fully mature in 15 minutes. very, very quickly.
Well, that kind of blew my mind because it feels like sometimes the storm comes through, it's like there's hours and hours of rain. How does
Yeah.
that-
That actually leads back to this here. And there's probably some better pictures of that. Actually, let me find one. Because that's a good question. Ah, this is good. This squall line moves through. So here's our convective line right here. And then, so this is the convective line. We call this the, oh my gosh, it just left my brain. Stratiform region. Stratiform region. So even if you're right here and this convective line runs through, it's going to be really intense for like 15 minutes. But then it's just going to generally, once you get into this area, just rain for like the next hour or two. But there's not a whole lot of like, you see the line here, that's where the severest stuff's going to be. But back here, it's just going to be just rainy, right? Maybe some intense rain at times, etc. And then once you get out of that, once this part passes you, then you're good to go. Like he talked about getting lunch for an hour. That's what this is indicating. Because once this all passes you, then you're pretty much good to go. You might be dealing with different winds, because out ahead of this, the wind's going from like this, and out this way, the wind's blowing from this direction, but yeah.
Gotcha, that totally makes sense because about a couple weeks ago we had a really big storm come in. There is that 15, 20 minute period where it's like, wow, it's pouring. And
Yeah.
it kind of levels off for a bit.
Yep.
Still left with some rain.
Okay, so we said that regular thunderstorms don't last very long, right? And the main reason for that was, here's our thunderstorm. You have your updraft right here, and then you have your downdraft. That downdraft hits the ground and spreads out laterally, making this gust front like this. Eventually, that gust front kills off the updraft, and you're left with no gas for your car. There's no more energy coming into it. The problem is, this storm is straight up and down. Every piece of it is straight up and down. What if we had a different situation? What if, I'm just going to draw a little wind here. So what if our wind was actually like this? What if as we climbed up into the atmosphere, you know, like 1,000 feet, 2,000 feet, 3,000 feet, etc., the wind was increasing in height? What if also the wind may be doing directional changes with height? So we call that wind shear, right? If we had a straight up and down storm, now our storm is actually getting pushed in the direction of the intensing wind, so we end up with something like this. Where the storm itself has now become tilted. So now our downdraft area is right here, and our updraft area is right here. So we've actually added some distance between our updraft and our downdraft base. This makes it a lot harder for our storm to kill itself off. And our storm can last 2 hours, 3 hours, 4 hours. An individual storm, not like a cluster kind of constantly regenerating. But an individual storm can last a long time. And that's what this is here. You can't really tell from this image, but this storm is actually tilted like that. So this is our updraft base. You can tell because it's nice and clean. There's very little precipitation occurring right here. Where's our downdraft base? Way back there. Way back there in the distance. That's where all the rain's falling. The other way we can say, we call this a wall cloud, right here.
What cloud?
A wall cloud. This is like our updraft base that's actually lowering. A tornado would end up coming right out of that if we were going to end up having one, or a funnel cloud. And this right here is very cool. This is called a tail cloud. The tail cloud goes from the updraft base and points back towards the downdraft base. That's because all this rain hitting the ground over here, this updraft base is pulling in all the air that it can from all directions. And the air over the ground over here, where all the precipitation's falling, is actually going to be quite moist. So it's pulling that in as well, and you're getting some condensation because the air right here is more moist than than the air over here. So you're getting a little bit of a tail. Pretty cool, but look at our striations. Like this whole thing is rotating.
It's just an amazing looking.
It's amazing, yeah.
It's like something from a different planet, like a Jupiter storm.
Yeah. See, I miss this so much because this is what my graduate school was just going out for 3 summers in a row and just getting in front of these things, putting down instrumentation is just a blast. People always ask, were you scared? But the tornadoes didn't scare me, it was the lightning. Because when you're putting instrumentation, like he's in a spaceman outfit, but when you're down here putting instrumentation in front of these cells, you generally know where the tornado is going to be and all that. And the hail core is going to be in a certain location, but the lightning's just hitting all around you. And it's really just a roll of the dice if you get fried or not. So you're just putting we're not heroes out there, but we're putting, we're all out there at our own whims. So looking at it from a textbook standpoint, here's our wind shear, right? You've got weaker winds at the surface. You've got stronger winds aloft. So you're creating this rolling tube of air on the surface of the Earth. And then along comes maybe a little cumulus cloud that decides it wants to be bigger than it is. So it develops an updraft and it starts growing, but it grows right over one of these tubes of rotating air. So then it takes this rotating tube of air and now it turns it vertically. And now your updraft is not just called an updraft, we call it a mesocyclone because it's a rotating updraft, like this. And not only that, but then your storm is also, they don't really indicate it here, but your storm is also going to be tilted because of that stronger wind at the top. So that's how you get your rotation, and that's how you get your tilt. Both very important for a supercell, because a supercell lasts for hours. And then we're not going to go into details here, but generally out pops the funnel cloud of the tornado, but that, this isn't officially a meteorology class, so I'm trying to keep it more to pilot stuff, or stuff you'd see. If you looked at this on radar, reflectivity, velocity, your radar in both of these locations is actually off the screen to the southeast here, so it's actually over here. Here's our reflectivity. You always say look for the hook. That's because this whole thing is rotating like this. Most intensely right here, this is where your tornado is going to be, if there is one. When you look at a tornado warning, they'll generally say like tornado on the ground, radar indicated. That means that no one's spotted it yet, but radar strongly indicates that a tornado is likely there. That's why storm spotters are still very important to the National Weather Service. Like calling in when you see a tornado is very, very valuable information to them because then they can confirm what the radar is actually telling them as well. But you can see the hook, and if you look at velocity, our radar is down over here. So green means it's moving toward the radar. Red means it's moving away from the radar. So you actually see you have a rotating couplet right here. And that's it for supercells. Any questions? You might get confused with the units over here on reflectivity. They're called dBz. And no, it's not an anime reference. But it stands for decibels as relative to Z. And Z is called a reflectivity factor. Again, not a meteorology course. Just go with your gut. Red, purple, getting into the whites here means bad. This means kind of bad. This means, light rain, precipitation, stuff like that. But I mean, again, eventually you might be in a plane where you have a radar in the nose of your plane. And there's tons of different kinds of radar, so I can't go over every single one of them. Maybe it's like phased array or magnetron or something like that. But the general principles are the same. It's just constantly scanning and seeing what the radar return is ahead of you as you're passing through it. Hail's very interesting. When I was teaching up at Texas Tech, we went storm chasing all the time. We would go out and we'd collect these giant golf balls plus baseball plus grapefruit-sized hailstones, and we'd save them, and I'd freeze them so that in class I could actually cut it open and you could see the rings on the inside. This is not my image, by the way. But you could see the rings on the inside. We also, we were in our early 20s, so we'd make hail garitas out of them. They're a little dirty because you're just dealing with this like dirt, ice that was on the ground, but so good times. How does a hailstone form? Well, you get rain droplets here. Let's say our storm is very, very, very strong. The updraft is really, really intense. So these rain droplets get sucked up above the freezing level and they freeze. They make a little ice like a grapplestone, little ice embryo. Then it kind of does this little rotate here, gets caught in the downdraft, but then gets re-caught back in the updraft. Once it crosses this freezing level and back into the water, it gets a little coating of water over it. And then it gets caught in the updraft and comes back up here and freezes again. And it just keeps doing this cycle over and over and over again, and you're forming these freezing rings around the hailstones. Eventually your updraft is not strong enough to sustain that ice anymore, that hailstone, so then it just falls out. So you see pictures of people having grapefruit-sized hailstones. I mean, that thing was in the storm for a long time. That means the updraft was strong enough to keep this bowling ball-ish object in the air for that long. That's crazy. Do you want to be flying in through an updraft like that? I mean, that's probably on the order of like 100 mile per hour updraft or something like that, straight up. That's just crazy.
How long does it take for big, pieces to form?
15, 30 minutes? Yeah. It can be pretty intense. Austin gets a lot of it too. I live on the south side of Austin. We generally don't get a lot, but I mean, up next to Pflugerville, North Austin, they've just gotten hit by giant hailstones the past couple years. Couldn't give you a meteorological reason why, but gotcha. Uh-huh. And the last little topic here before we move into weather maps and like what I would do to forecast are downbursts. I'd say out of anything flying, this makes me the most nervous because it can be, I mean, you would expect that giant towering cumulonimbus cloud over San Marcos to be dangerous. And you're right, it is dangerous. But you could also have this cumulonimbus calvus, this storm that looks kind of dangerous, but you're like, oh, it's not fully developed yet or whatnot. It's probably on the safer margin. And it all of a sudden just drops this massive downburst or microburst right over the location. Dynamically, it's just not something you can tell just from the outside of what's going to happen. But it's like the downburst here, the downdraft initiates and it just drops all of its cold, dry air at once. Or it could be precipitation loaded and all the precipitation falls at once. So just very sudden here. Like that's so dangerous. That has taken down planes before. And we'll get into an image here that was actually made for a law case back in Dallas. But the general gist here is you get this big cold air downburst that breaks away from the cloud and hits the ground. And then once it hits the ground, it spreads out laterally and creates these vortex rings on either side. When you read through your pilot's handbook, they talk about the different kinds of radar in the weather section. The WSR-88Ds here are really general purpose radars. They're S-band like we talked about. They're made to see pretty decent long range, so they can't really see as good of detail. But they make special radars that are around major airports like Dallas or Houston. They're called terminal Doppler radars. They have a very short range because they can see a whole lot better detail. And the whole purpose of those radars is to start seeing stuff like this. They update a lot more frequently. They're like 1-minute updates. And they're specifically looking for these sudden bursts of air that can hit the ground and cause planes to crash. And here's I think this was based on there was a Dallas airliner that crashed back in the mid-90s. And this image was created as part of that whole legal process at the end of it. But the pilots came in and you start hitting the edge of this gust front, and this gust front's pushing the pilots, it's pushing the plane up, so the pilots are actually trying to keep level, so they're nosing down a little bit. And you get into this area here where you're not really feeling this upward push of air, and all of a sudden you get into the downburst area. Well, what was your orientation for your stick? You were nose down, and it powers out, yeah. And then all of a sudden you just get absolutely blasted by this like 100, 120 mile per hour downburst, and you just nose down. Very hard to recover from, I'd imagine, because I don't know how to fly one of those things. But yeah, just very dangerous. So that scares me. When I'm at the airport and I'm on a commercial airline, I remember when I was flying up to Seattle back in 2017, and I was at Houston, and we were loading the plane, and there were thunderstorms everywhere. I was an absolute nervous wreck, because I was like, yeah, I get to go fly in some some severe weather, which is cool, but I was just terrified and just hoping that the right people were at the controls to know when to call it. So
That's, as a result of that particular accident in Dallas, this is a scenario that's trained in a simulator a lot.
yeah. So if you get canceled for weather, your flight that you're trying to go visit family or something like that, I mean, don't get mad. And don't get mad that if other planes were canceled because of weather in a different area, then your plane didn't arrive. I mean, it's all connected, and it's all just to keep people safe. So, all right, any questions on severe weather? Probably tons, right? But that's all right. What do I look at for weather? Very first thing, aside from just kind of looking at the weather briefings and whatnot, I love this website. So the next 30 minutes here to close out, we'll just go like, I'm actually flying today, but I'm also planning on going to Fredericksburg tomorrow, so we can kind of see if that flight to Fredericksburg is looking good tomorrow. Tropical tidbits. This is a great place for you to go to get some weather snapshots. Also a really great place to go to get models. So weather models are very cool.
Let me just create something. Tropical tidbit is
Not official.
Legal weather briefing, but it's a great place to go. But you still need to get a legal brief. Right? Everybody knows what that means. Okay.
Yeah. So a weather model, we have a bunch of different kinds. I kind of use both spaces here on the other side of the board. You can have global models, which there are the GFS, Global Forecasting System model. This is the North American model. You can also have the ECM WRF. This is the European model, widely considered more accurate than the GFS model. Unfortunately, the North American model it's good to look at, and sometimes it's right, but more often the EC is a little bit more accurate. And this is only getting worse because they're defunding, and they actually laid off a bunch of the atmospheric scientists that were working on it when Trump took office. So take that as it will. But this is actually going to get worse in accuracy over the next 4 years. So these are our global models. They're made to look at the entire globe. They have a very, very low resolution. And what I mean by that is if we have our United States here, I'm just kind of emphasizing this. You have a grid point system like this, where the weather model is trying to forecast weather variables at each one of these little grid points here. Global models have very low resolution, which means the space between the grid points is pretty big. Pretty big. If you have a high-res model, so you start getting into the mesoscale models, mesoscale models are more like, hey, let's really zoom in and look at what's happening in Texas. So you're looking at a much finer resolution. Here, you might be getting, that's terrible. Purple. You're essentially adding some more grid points here. So now instead of just like spacing like this, you have much stronger spacing of the grid points. So you're increasing the accuracy and you're increasing the resolution. Everyone cool with that? All right. So, tropical tidbits. You can come to this website. You can come over here to forecast models. And you're left with a screen like this. So what do we see? You see the current model that you're looking at. So this is a global model. Here's all your global models. Here's all your ensemble models. Ensemble models are, instead of having, let's say we're trying to predict temperature out. So this is time. And let's say we only use one model to do it. And our temperature here is going to be, we're going to get hot in the afternoon, we're going to cool down, hot in the afternoon, cool down for evening time, whatever. This is a typical diurnal cycle of temperature. But instead of just having one model doing it, let's say you had 50 members of that ensemble all doing it as well. So you have a bunch of different runs, like 50 runs for it. And then what you can do is you can take the mean of all of those and kind of, that'll probably make a good representation of what the temperatures are going to be like. Or maybe one of your little ensemble members here was crazy. Maybe it was like, oh, we're going to get up to like 120 degrees. And you're like, oh, it's way out in left field. But then it happens. And you're like, oh my gosh, well, we had like a 1 in 50 chance of that happening, and it actually happened. So that's what an ensemble model is. You have your hurricane models, and then most importantly, you have your mesoscale models. Any questions yet? All right. If we click global, you can see the list of all the models that you can see. ECM WRF is going to be your European model. GFS is going to be the North American model. CMC is going to be your Canadian model, and JMA is Japanese, which I'm actually kind of surprised it's here. It's probably not a whole lot. They're very secretive with their weather information over in Japan. It's very hard to get a hold of. Contrary to the US is very open source with its weather data, very public, which is very nice. So really the only ones you're going to ever look at for these are going to be these two right here. We'll click on mesoscale now. And we can see a bunch of different ones here. The only one I really want you to focus on is the HRR, the HRRR. This is the High Resolution Rapid Refresh model. It generally goes out 12 hours to 48 hours ahead of time. So while you can't use this as an official briefing for what your weather's going to be like, before you fly, you should most definitely take a look at the HRRR and see what's going to happen. This runs every single hour. So it initializes every single hour, and it goes out a certain amount of time. So we'll click on it. And you can see this particular run, it ran 15Z. So that's 15 UTC. What do we have to do to that to get our number, or our time? Subtract what? Subtract 5. So this ran 10 o'clock, 10 a.m. This is the 10 a.m. run. A little bit late. I mean, we're 11:38, so the other one's a little bit on the late side. I think he's been having some internet issues with his stuff. So, but this runs out 1, 2, 3, 4, 5, 18 hours. It goes out. So we can see 18 hours in the future from 10 a.m. See what the weather is going to be like. You can click it, and you can go back in time to look at the 12Z run. Meteorology is very heavily favored to the 0Z, 6Z, 12Z, and 18Z. Like when you break up the day into 4 different major forecast hours, meteorology loves that. That's what we kind of live and thrive for. So if we go back to the 12Z run, we can actually see further out than we normally would. Look at how many hours we gained. We can now look out 48 hours into the future. Whether you want to look out go back and look at, because if we go back 3 hours, we're kind of assuming that the weather model might not be as perfect, because that's 3 hours of information that we no longer have. But maybe that's something you want to look at so that you can see further out into the distance. Does that make sense to everybody? Okay. The last little thing before we start looking at stuff, you can come down here to regions, click it, and change to have a better picture. So we can click on South Central US and zoom in to Texas. So let's come back up here, make it the most accurate as possible. We'll go to 15Z. And now we have here a picture of Texas and what the weather is going to look like. So it's saying right here at 10 a.m., we should probably have some little bitty cells that are kind of popping up along the Gulf Coast. So let's look at the radar. And I got to change this back to reflectivity. So there's Corpus's look. Here's up here, this is the radar right here at our location. And then here's Texas. So do we have some little showers coming in off the coast? Yep. So that verifies. I would say that's very important. If you're going to start trusting the model, look at what the model is predicting for right now and go look at the weather, the radar. And if what it's predicting doesn't match up, then that run probably isn't going to be very accurate, right? It needs to capture what's going on right now very perfectly, I would say. Now, the question is here, I have a flight later this afternoon, we'll say, it's like 5 or 6 o'clock. So as we get closer to that time period, are we going to have some storms here in the area for us to worry about? This was initialized up here at 15Z, so what's that, 10 a.m. Forecast hour, it's valid at 18Z. What's 18Z? 1 o'clock. So this should be what the weather looks like at 1 o'clock. So if we progress forward to, if I want to fly at 6 o'clock, what time should I look at for valid? What is it? 23? Good, yeah, because 23 minus 5 gives us 1800, which is 6 o'clock. Good, look at that. This is saying that we're going to have some little popcorn showers, and it's actually indicating one. Here is, this is Bexar County, so this is San Antonio. And we are, here's Austin. And you know, we're about like right here, right along I-35. So this is saying like right over here next to San Marcos, we're probably going to have a little cell that develops around 6 o'clock. I would look at this and say, hey, I actually have a chance here of going and flying, and there could be some, actually it's got a little bit of a red. If you look at the reflectivity, I mean, we're getting into some of the reds here. So actually this could be a pretty decent little cloud of vertical development. So definitely something to watch out for. Pretty cool. You can also click. You can click anywhere on this map and get a vertical forecast sounding for the location. So let's click right here, right where New Braunfels is, and we'll generate our sounding. And I can see what the wind is going to be at the surface. So that's a 10-knot wind out of the southeast. What is that? Probably like 1 out of 160, 150, something like that.
So it's just, does this sounding correspond with the 1800 Zulu time that you had when you clicked it?
Oh yeah, this is valid for 23Z. So this, the weather data feeding into this was generated at 10 a.m.
Right.
And it's saying that this is what the vertical atmosphere is going to look like at this point,
Right.
at 23Z.
So if we went back to right now, it should give us a sounding of
What is that?
theoretically should be right now.
Yes. So we'll actually set it for 17Z there. So 17 minus 5 gives us 12. So this should be what the atmosphere looks like right now. Look at how close our temperature and dew points are here. While they're not touching, probably a good indication that there is some cloud act there. What do we got outside? Pretty decent.
Yeah.
In fact, let's use an official source here. We'll go to aviation weather and we'll type in KBAS. And we'll see that we've got few at 2800 as of 10:51.
Does
2800 AGL.
that correspond with what you got?
Yeah, so let's say, I don't have like a good vertical line here to look over, but let's say about right there. So around 850, 900 millibars. So right between these, actually like, 850, 900. So right around 1 kilometer up, which we said that 1 kilometer was 3,300 feet. Pretty good.
Yeah.
Pretty close. Oh yeah, I was on the website. So pretty nice. What's our wind direction right now? Pretty much directly out of the south. What you'll notice, if there's only 5 knots, it won't have the flag at the very end. It'll kind of bring it in a little bit and then tilt it. So that indicates 5 knots right there. What's aviation weather saying our wind speed is? Variable 6 knots. So, pretty awesome.
And that was forecasted when?
That was at 10 a.m. So pretty good, right? This is a good way of, like, especially if you wake up in the morning and you're flying at 10 o'clock or something like that, have a look at this. Just kind of see what to expect for the weather that day.
So that forecast came out at 10 for
right now. Yes. But you could look at this, I mean, you could use an earlier run too if you wanted to look at. Just, it's pretty obvious, but I'm just going to state the obvious here. The further you get out, the less accurate the weather's going to be. Reminds me, I get jokes all the time as a meteorologist. They're like, oh, you get paid to be wrong, right? Or I get all the jokes about, oh man, if I was wrong 50% of the time, then I wouldn't have a job, et cetera, et cetera. The weather forecast is actually right like 9 times out of 10, probably more accurate than that. But like 99 times out of 10 or 100. But you only ever remember when the weather forecast was wrong and it inconvenienced you. You don't remember it's selection bias to it, right? You're predicting what all the air is doing with all the billions of feedback mechanisms on the planet, with all the different lakes and oceans and all this stuff. The fact that we can even predict the weather 24 hours out very accurately, which is true, by the way, is a marvel. It's a marvel. And with the advantages of cloud computing and stuff like that coming in and like quantum computers, that's only going to get even more accurate in the future. Everyone, remember that Back to Future 2, where he like looks at his clock and he's like, the rain's going to stop in 3, 2, 1, and then it stops. I mean, maybe one day we'll hit that kind of thing, but that'd be pretty cool. So that's what I look at. That's what I look at. Now if I want to look at tomorrow, so say I'm actually going to Fredericksburg tomorrow. I'm going to try and go to that diner for lunch. So let's see if the weather forecast for tomorrow looks really good. Now this is still the 15Z run, and as far out as I can see, I can only see 9Z on Sunday. So what is that? -5 gives me 4 a.m. I can only see to 4 a.m. tomorrow. Does this help me if I'm flying at 10 a.m.? So I'd want to see what the weather's doing at like 11 a.m., something like that. But what I can do is I can step back 3 hours and look at that 12Z run from earlier this morning because it goes out further. And then I can take a look at, there, we'll look at that. We'll look at 12. Pretty clear. Pretty clear here. We're having pretty much the same thing as yesterday. We're just having some storms along the coast. What's the wind? Here at New Braunfels, I'm taking off at 5 knots from the south. A little close here though. We're probably going to have very similar cloud cover to what we have right now. Probably few, maybe scattered at like 2,800, 3,000, something like that. Which does make me a little bit nervous because if I'm going out west to where all the terrain is actually increasing in height, right? I'd also want to fly higher because it's complex terrain and there's not a lot of safe places to land, so I kind of want to be safe about it. Maybe this doesn't look good for tomorrow. Maybe I want it to be a lot more chance of clearage to be able to fly higher. We go a couple steps forward. Does it get better? Kind of. Actually, it does. Yeah. As we go through the day, this temperature is going to keep increasing like this, and that's going to pull this line further this way. Now, we could have a big blast of southerly air bring in some moisture, and that would cause our dew point line to increase to the right as well, so that could cause a situation. I shouldn't just look at here, though. I shouldn't just look at New Braunfels. So 12 o'clock. I should also come up here and look where Fredericksburg is. You can see our lines here are a little bit further off the bottom because they're higher elevation than us. Pretty good dew point separation, but again, we still have probably some few, maybe some scattered clouds there. And look at my winds, straight out of the south. If I recall, San Marcos's, or sorry, I shouldn't say, but Fredericksburg runway is oriented kind of like this. So if I'm having a south wind, then I can start planning on which direction I expect to make landing, which I think Fredericksburg is right traffic at this point, so. So cool. Any questions?
So if you pulled a skew T in Denver, those lines would start up at 5.
Oh yeah, let's draw it. So that's where we are at T82. This isn't an artifact. This isn't a problem, right? It's just they're at a higher elevation than us. Again, and you can see the wind barb. You know, it kind of shows the, if you look at the average location of where that wind barb is, like right in the middle, then you can see where it actually lines up with the surface. So very cool. I wouldn't worry too much about this stuff over here. I wouldn't worry about equivalent potential temperature. That's getting really detailed. Photograph is kind of interesting. It's showing what the wind's doing as you go vertically, but again, don't worry too much about it. All of these numbers over here probably don't mean anything to you, and that's okay. You don't need to worry about them. But very cool. And there's other websites that do this. So this isn't the only one.
I'd like you to do a class on skew Ts.
Yeah, SKUTs, it's super fun. There's so much you can diagnose because all of these numbers over here are generated automatically. But you can go in here and you can, based on some tricks with all these lines here on the graph that you can probably barely see, you can actually diagnose where every single one of these levels are. You can find the LCL, you can find the level of free convection, you can find the equivalency level, all sorts of really cool stuff. Soundings are so much fun. Again, remember it's a forecast sounding though. It's not an actual sounding. So, you know, it's just not perfectly accurate. The other thing I would also like to point out is, do I have Texas still drawn? Kind of, not really. Don't make fun of me, y'all's Texas probably is even worse if you drew it, right? We like to think that if we launch a weather balloon from here in Corpus, that weather balloon didn't move laterally in any direction and went straight up. In actuality, that weather balloon that they send up moves just as much laterally as it does vertically. So if it goes 30 kilometers up into the air, which it does go all the way up in the stratosphere, you can bet that it actually drifted 30 kilometers in some other direction. So it might have done something like this by the time it popped and fell to the ground. So even that sounding right there is not 100% accurate to what the vertical column of air is above. So even if you went over here and you looked at it's been a while since I've looked at actual soundings, but what's my favorite website for this? 2. Oh, Corpus didn't launch one today. So this is an actual sounding. This is a real weather data that went up. And you can see down here at the coast, pretty close together as far as the dew point and the temperature goes. So probably some cloud layer at the surface, which you'd expect in the morning on the coastline. And then as you go up, you can see it's kind of a very mixed atmosphere, a lot of jumping around. And then here's what the temperature does. So I was just saying, like, even if you look at this, which you know and you want to believe is true, it might not represent the actual vertical perfectly column above the surface. And I think that's all I got today. So,
All right.
no problem.